your sort of sign-in screen on my switcher over there, so get loaded up, and then I'll switch you over on the main screen.
Yeah,
But that'll show exactly the same
same as
on
that
the
one.
main screen there.
It's just a single HDMI display. Why is my mouse not working? Okay. Okay, so the second display is active. If I go to this one and then move this one to that one,
Just go and switch you over. There's a clicker there if you need it. I don't know.
does it actually work? Yes, it does.
Give him a warm welcome.
Thank you, everyone. So, quick introduction about myself. I've been a Rust user since about 2014 and a member of the Rust project since 2019. I'm currently co-lead of the library team. I also led the inline assembly project group. You may also know me from some of the crates that I maintain. The most well-known are probably Parking Lot and Hash Brown.
Shush, please.
So let's get to the meat of the topic. What is an ABI? Why is it useful? And what does it mean for it to be stable? So before we talk about ABIs, we need to talk about APIs. In the distant past, software was built as a single monolithic piece, just running on bare metal, You have a single unified code base, and you don't need to worry about other people. Think like the Apollo moon lander. Today, this doesn't really work anymore. Software is multiple orders of magnitudes more complex. You now have to actually interact with other people. Oh, the horror. You have different teams that are working on different components. These teams may be on the other side of the world, etc. Belong to different organizations. As an example, consider just a Hello World program running on Linux. Seems nice and simple. Well, you have your code, the Hello World program, that needs to talk to the Rust standard library written by the Rust team, which needs to talk to the C standard library written by the glibc team, which needs to talk to the Linux kernel, which is maintained by the Linux kernel maintainers. The API, application programming interface, is how all of these components talk to each other. It defines the interface between two components and as the set of data types that they use to communicate, all of the functions that are exported by one component and that can be called by another component. Conversely, and very importantly, the API also implicitly defines what is a private implementation detail of a component. These are the parts that you are politely asked not to directly observe and modify. In the good old days of, I think, MS-DOS, you just, yes, I know I'm not supposed to touch this, but I also know that this library at this very specific memory address has this thing, so I'm going to poke that directly. This will completely break when that library is updated. And that's the important part about APIs and about these components, is that APIs allow components to be interchangeable. As long as both sides properly follow the API, I can just take one component and substitute it with another component that has the same API. Usually that's a newer version of the same library, but it could also be an alternate implementation, which has completely different internal implementation details, but the same API. So let's talk about Rust. I trust everyone in this room already knows this. In Rust, the unit of compilation is a crate, usually a library or a binary, and this corresponds to a component in the API model. So crate consists of a tree of modules with different items, some of which can be public. Anything that is public at the crate root is exported to other crates, and this is the API of a crate. So what is a breaking change in the API? That's when you make a code change that results in violating the API contract. So in Rust, the rule of thumb is as long as the change you make can't cause any code to fail to compile, any code that previously compiled failed to compile, then it's not a breaking change, it's fine. Let's just look at a few examples here. Consider this function that's exported from crates, and therefore part of its API. If I change the signature of the function by changing its parameter types or return value, then, well, downstream crates that try to call this function will get a type error because they're passing the wrong type to this function. However, it's perfectly fine to change the implementation of the function since that's not part of the API. Of course, within reason, if your function is documented to multiply value by 2, don't actually change it to multiply value by 3. So let's look at another example. This is a struct with one public field and one private field. I can't change the type of the public field because it's accessible by downstream crates, and if I change the type, those crates will no longer compile. However, I can freely change the type of a private field because there's no way that other crates can access this. It's private. Once again, be reasonable. If you have documentation guarantees that says this struct is exactly 8 bytes, don't change the layout. Let's look at a more interesting case. What if we have a struct where all the fields are public? Can I add a new field to it? After all, I'm not changing anything. I'm not removing something that's public. And the answer is no, because code can use, Rust has destruction syntax and struct construction syntax, which require all fields to be specified. And if you don't, you get a compile error. So yeah, you can't add a new field because this causes a compile error. This code on the right will no longer compile. However, there's a way around this, which is the non-exhaustive attribute, which means that downstream code cannot assume that it sees that the fields are exhaustive, which allows you essentially to add new fields in the future because you know downstream crates cannot rely on all the fields being present. I promise this will be relevant later. So let's take a step back and talk about the Rust compilation model. Rust crates are compiled from source code into rlib files, which are in intermediate formats, which contain compiled code and API metadata. This API metadata is used by downstream dependencies. For those of you familiar with C, an rlib sort of acts like both a compiled object file and a C header file. And once all of the crates in a program are compiled, they're just linked into a single output binary. In this case, you get ripgrep, which is built from the ripgrep code, which uses the regex crates, which uses the standard library. And Rust currently requires all of the crates linked into the same program to use the same version of the Rust compiler. Now, remember what I said about APIs. It allows for component substitution. Here, the substitution happens at the source code level. I can take the source code of the regex crate and replace it with the source code of a newer version of the regex crate, and this will continue to compile, as long as this new version maintains API compatibility. Same thing with the standard library, etc. So what does this look like if we have a stable ABI? So the main thing that stands out now is that instead of linking all the crates together into a single binary, now each crate is compiled to a separate binary artifact. Library crates are compiled to shared libraries, and the program is compiled to a program binary that has a dynamic dependency on these shared libraries. This allows us to perform a crate substitution at the binary level. I can now take these compiled artifacts and substitute one shared library with a different shared library. The interface between these binary components is the ABI, application binary interface. The same concepts of API stability and compatibility apply to the ABI, but they differ in some key ways, which we'll look at later. So another point that stands out, you'll notice that we can now use different Rust C versions for each component because they have a stable API, and the Rust compiler will guarantee that these artifacts with stable APIs will continue to be compatible with older versions. And this is essential because we want newer versions of our crates to be able to use new language features as they come out. So let's take a deep look at what exactly do we have inside this ABI stable crate binary. So it mainly consists of two parts. The first part is the crate metadata, which is everything that Rust-C needs to, it's everything that's used to describe the public API of the crate to Rust-C so that you can build other crates that depend on it. And this is similar to the existing metadata in rlibs, except that it's guaranteed to have a stable format. And this will include things like type definitions, function signatures, constants, and even crate documentation. You can pass this shared library to RustDoc, and it will just generate the documentation from this metadata. The second half is the actual compiled code that's used at runtime. And this only includes minimal metadata used by the dynamic linker for symbol resolution. So one thing that you can do is split these two parts after compilation. For example, the most common case would be to strip out the metadata if you're tight on disk space. For example, you want to ship this on a phone, and you're never going to run Rust-C on a phone, usually. Some people, you know who you are. So to save on disk space, you just strip out the crate metadata and only keep the runtime portion. A stable ABI allows components to be substituted at the binary level. Why is that important? Well, there's several important use cases. The first one is that it allows you to ship pre-built binaries as part of an operating system. Think Android or a Linux distribution. It avoids code size bloat in applications. Now, the Rust standard library is just shipped as part of the operating system. Each app doesn't ship its own copy. It's also useful for security updates. If there's a security issue with one crate, you just update that one crate. Done. You don't need to recompile the entire world. Another thing you can do is to support frameworks, such as game engines, which include what I like to call plugins, user extensions. The game engine could ship with a precompiled SDK, on top of which you build your game. And then the stable ABI would guarantee that the game you built works with future versions of the game engine, and that you can use the latest Rust-C version, no matter how ancient the Rust-C used to compile the game engine is. Okay, so let's recap what we want to achieve with a stable ABI. Library crates should be compiled to shared libraries with a stable ABI, and these should be backwards compatible with older versions of the same library. Compiled crates, which use an ABI stable library, should be forward compatible with future versions of that library. Crates compiled by different Rust-C versions can be freely linked together. This means that not only must Rust-C be backwards compatible for older crates, it also needs to produce forward compatible crates. And finally, we want to keep the concept of ABI stability simple by tying it to API stability. That's something that Rust programmers already understand quite well. The idea is that as long as you don't make any API breaking changes, then the crates are ABI compatible as well. So why is this such a hard problem? We are now almost a decade after Rust 1.0. We still don't have a stable ABI. Why is this so hard? Well, there are two fundamental challenges. The first one is that there's a lot of implementation details that Rust doesn't really specify. Things like the default calling convention, how we do symbol mangling, struct layout, enum layout, vtable layout, and the crate metadata format. And the main reason why these aren't stable, and it's a good reason, is that we want to leave ourselves open to improving these in the future. If we stabilize these as they are, we are effectively closing the door to any future opportunities to have a more compact layout algorithm, have a better crate metadata format, etc. The second challenge is that at the binary level, implementation details of one crate will tend to leak into another crate, even though they don't at the source code level. For example, if a type has private fields, we can still move it around by value, but in order to do this, the compiler needs to know how big this type is and how much space to allocate on the stack for it. But that means that now you have compiled codes that assumes that this type has a specific size, which may no longer be true in the future, because remember, you can always add more fields in the future. That's not an API breaking change. Another example is inline functions and generic functions. And the implementations of these functions are private implementation details. However, fundamentally, due to the way they work, due to the way generics are implemented and due to the way inlining works, the compiled code is embedded in a different crate than the one it came from. So let's take a step back and see how other languages have tried to tackle this problem. Let's talk about C. C standard says very little about the ABI. It doesn't actually even tell you how big an int is. However, thankfully, it's such an old and widespread language that most platforms have an actual platform ABI that specifies this. And it also specifies things like calling conventions, symbol mangling, type layout, etc. C programs are typically structured with header files that contain type declarations and function prototypes, and leave the actual implementation of these functions to the individual C files. Now, these header files are exported for use by other libraries, and if that effectively means that the header file defines the API of a library. Now, C has no concept of privacy, which means that everything in the header file implicitly also becomes part of the API. This includes any inline functions, and, well, as I said, there's no privacy, so there's no real concept at the language level of private fields. Quite reasonably, there are a lot of C libraries that don't want to expose these internal details, and they have to use awkward workarounds for this. For example, the file pointer used in C is an opaque type. You can only access it indirectly via a pointer. The header files don't tell you anything about the actual I/O file structure. Alternatively, there's semi-opaque types where the header file will tell you how big a type is, but not actually give you access to any of its fields. There's also the convention of using underscore prefixes to politely ask you not to look too deeply into this. It was an early language. It's a good attempt. So, C++. C++ extends C with many features, like object-oriented programming and templates. As with C, there's no standard ABI, but it's instead defined by the platforms. Now, C++ still uses header file, but actually has a concept of privacy. However, this only works at the API level. Any private fields in a header file, even though you can't access them with the code, they still become part of the ABI because it affects the size of types, and that assumption is encoded in the code that is generated. You can work around this using, again, some form of indirection by just doing everything through a pointer. It's a hassle. C++ also introduces templates, which are like Rust generics. However, all template functions and types must be included in header files because, again, the code is only generated when you use them, not when the original library is compiled. This has unfortunately led to many C++ libraries just being entirely header-only libraries, where they just ship header files and not an actual library, because it's just too much of a hassle otherwise. Let's talk about Java. Java just avoids the problem entirely because they just move code generation to runtime. So Java code's compiled in 2 stages. The first stage is an ahead-of-time compiler that generates Java bytecode within Java class files. This is a stable format, but doesn't contain any actual executable code. At runtime, you have a JIT compiler that actually translates this into actual machine code. The Java bytecode is quite abstract. It only refers to fields by index, so Java bytecode is essentially load field index 2, and at runtime, the actual ABI is determined, and the JIT compiler will transform that into an access of a certain offset from a pointer. The JVM is free to rearrange the runtime layout of things, is free to inline across class boundaries, doesn't care, it's all at runtime. Everything is known at this point. The downside, obviously, we'd love to do this in Rust, but we can't really. We don't want to, really. Generating code at runtime is somewhat slow. It's also impossible in some platforms like WebAssembly or iOS, and it's impractical on many other platforms like embedded systems and OS kernels. Swift is a rather interesting case. It's a language that was designed by Apple, released around the same time as Rust 1.0, and it shares many features with Rust, like static compilation and trait-based generics. More importantly, Swift version 5, released in 2019, introduced a stable ABI. And Apple used this to essentially ship the Swift standard library as part of the operating system. And this worked out relatively well. It helped reduce the size of applications, it allows for independent updates, and the rest of the proposal for a Rust stable ABI, that's going to be the rest of this presentation, is heavily inspired by Swift design. They did a really good job. So, congrats to them. So, let's get into the main topic. How can we design a stable ABI for us that addresses all of the challenges that we discussed earlier? First of all, some disclaimers. This is not an official position of the Rust project. This is an exploratory proposal. It's not implemented yet. It's still subject to change. What color would you like your bike shed? So let's get back a few slides. I listed a set of implementation details like calling convention, etc., that we need to fix. Well, in a sense, this is the simplest part of the problem to address. Just pick a format and stick to it. We need to do this very carefully because once we do that, we can't change it anymore. But it's a relatively simple problem to solve. The crate metadata format is particularly important because we need to design a format that's extensible and that is able to describe any future Rust language features that we may add in the future. But it's still a relatively simple problem to solve, so we're not going to talk about it. Let's instead address the other half of the problem, which is more complicated to solve. It's the fact that implementation details tend to leak across crate boundaries. Consider this example where crate A defines a struct, and that struct is then used in crate B. So it's always a break and change to modify, remove public fields, and since all of these fields are public, it's a break and change to add new fields. And finally, this is a bit of an obscure detail, it's also a break and change to add a drop implementation to this type, since that prevents the use of the destructuring syntax. My point is, we know that the layout of this type can never change. It will always have these fields. And therefore, we can just, when we're compiling crate B, we always know what the size is. We always know what the alignment is. We always know the offsets of the various fields. Therefore, the compiler can just embed that assumption into the code, because even though it's defined in a separate crate, that type can never change, so it's fine. Now, this becomes a bit more complicated when private fields are involved. These fields are private implementation details. In the future, I can add more fields, remove them, change their types. Now, when we're compiling crate B, we don't know the size of this type, we don't know the alignment, we don't know if it requires any work when it gets dropped. We don't even know the offsets of the field, because Rust will reorder struct fields as needed to obtain a more compact struct layout. How can crate B work with types that it doesn't know the layout of? And the solution is for crate A to export a type descriptor, which contains all of the information needed to work with this type. So this includes the size, the alignment, a drop function, and niche information, which we will ignore for now and get back to later. The type descriptor is exported as a symbol from the shared library for crate A, and crate B will just import that symbol, and the symbols will get resolved by the dynamic linker at load time. The offsets of the different fields are also exported as symbols. We don't include these in the type descriptor itself because reordering fields is not a break and change in Rust. And therefore, reordering fields should not be an ABI break and change either. We rely on the dynamic linker to resolve the offsets by name rather than just adding them after the type descriptor at some offsets. So how does crate B actually make use of this type descriptor? So since the size of this foo type is not known at compile time, we need a dynamic stack allocation, which uses the layout information from the type descriptor. This is relatively cheap operation, only a handful of instructions. Then we need an adapter function to actually invoke the new method on foo. We can't call new directly because new returns this type by value, and the calling convention requires us to actually know the size and layout of a type if we want to pass it by value. So instead, we need this adapter function that passes the type by reference and essentially translates the calling convention from one that passes by value to one that passes by reference. Then we access the bar field using an offset, the offset that's from the exported symbol. And finally, we call the drop function in the type descriptor to actually drop the type once we're done using it. There is a slight complication. What if we have two library crates, one of which defines a type, sure, and another one defines a different type that includes the first type as a private field? How do we calculate the type descriptor for that? We can't we can't determine this ahead of time because it depends on information that we will only know at runtime, which depends on the version of crate A that is available when we actually run the program. So what we need to do is to initialize the type descriptor on program startup when the crate is loaded. Let's talk about enums. So enums are easy in a sense because enum fields are always public. So normally an enum would be treated just like an exposed type, so a struct with all public fields. You don't need a type descriptor because the layout is known. Unless that enum is marked as non-exhaustive, in which case you can add new variants, and that now means that its layout is unknown, and you need a type descriptor for it. This works more or less just like type descriptors for structs, except for the enum discriminant, which tells you which variant is currently active. Rust currently encodes this in creative ways. So rather than just saying the enum is this field at this offset, we actually export a pair of functions to access it. Let's get back to the niche field that we conveniently ignored earlier. This information is needed to determine the layout of enums that contain this type. So normally enums consist of a discriminant tag, which is just an integer, and then a union of all the fields of the different variants. However, in some cases, we optimize the tag away by taking advantage of cases where the type inside an enum variant has unrepresentable values. For example, Rust references are never null, so we know that the bit pattern for 0 is always invalid, and therefore we can encode the none variant of an optional pointer as the bit pattern 0. And you can see it here that the size of an option of U64 is 16, but the size of an option of a box is only 8. Okay, why is this a problem? Well, if you have the function below, the generic function below that mutates some value of an unknown type, and the T can come from different crates, so via type descriptor, you need to be able to figure out what the actual type of this option is. And that's what this niche information is. So it makes the type descriptor computation more complex, but it's necessary for every crate to agree on the layout of a particular type. So at this point, we have a nice system for working with opaque types that have an unknown layout, and this makes compiled code resilient against layout changes in private implementation details. The next challenge is, okay, great, how do we make generics work? So generics in Rust are based around the concept of monomorphization, which means that generic code is actually a compile time template, and specialized instances of this template are generated for each set of type passed in as a generic parameter. Consider the example on the right. Crate A doesn't know what types are going to be used with the make pair function. Therefore, it can't actually generate any code on its own. It's only when crate B actually uses this function with specific types that the compiler actually knows which specialized instances of make pair it needs to generate. And that's a problem if we have a stable ABI, because we end up with the situation on the right, where the implementation of make pair ends up in the binary artifact for crate B, which is actually incorrect, because if you want to upgrade crate A to a different version, well, now crate B is using contains incorrect code. It doesn't match the code for the crate A that's actually in use anymore. So we need a different solution. And the solution here is polymorphization. Rather than creating a separate instance of a function for every type it's used with, create a single function that can handle any type by just having this function take a type descriptor as input for every type parameter it has. And this works out because type descriptors conveniently encode all of the information we need to work with an unknown type. So in this example, we have an identity function that just returns its argument. The polymorphic version of this is just copying the bytes from the input pointer to the output pointer. Since, if you remember, passing types by unknown types that are passed by value get transformed to pass by reference. And all we need to know for this is the size, which is from the type descriptor. If you recall, in some cases, we need to dynamically initialize a type descriptor at runtime when it depends on another type descriptor. And the same reasoning applies for generic types whose layout may depend on one or more generic arguments. In such cases, instead of exporting the type descriptor as a static variable, we instead export a constructor function that takes type descriptors as inputs and returns a new type descriptor for the output type. Type descriptors need a static lifetime. They need to be valid for the entire lifetime of the program. And this means that these constructor functions need to dynamically allocate type descriptors at runtime and keep them in the global registry. These are lazily generated and cached based on a template that tells us how to construct this type descriptor from the input type descriptors. Now, there's very little that generic functions can do on their own with just a generic type. Essentially, you can move the value around and then drop it. Not very useful. So most generic functions in practice include trait bounds, which allows the generic function to actually call trait methods and do things with a type. So in a polymorphic function, trait bounds are transformed into additional arguments pointing to a trait descriptor, in addition to the existing type descriptor arguments. So in this case, in this example, you can see the toString trait, which just defines a method. And you can see what the trait descriptor for toString looks like. It's just a struct with a function pointer it's just a function pointer for the toString method. And you just, and in the polymorphic print, you just call that passing the value by reference. So where do trait descriptors actually come from? Well, one of them is exported for each implementation of a trait for a particular type. The descriptor is exported from the crate that actually contains the impl block. So here you can see a more complex trait with an associated type, an associated constant, and a method. We've already seen how methods work. Constants are just directly embedded into the trait descriptor. Associated types are a bit more interesting. We can't just embed the type descriptor directly into the trait descriptor. And the reason for this is that in Rust, it's actually possible to construct an infinite chain of associated types. which would require infinite memory if you actually tried to represent it. So associated types are actually computed lazily. Let's look at a more complex example of a trait implementation where the impl block is itself generic. And this is similar to generic types, which have to, instead of exporting a direct type descriptor, export a constructor function that returns a type descriptor. Here, we need to export a constructor function that will create a new trait descriptor from an existing type descriptor and any trait bounds on that impl block. So as before, there's a global registry of trait descriptors because we need to allocate them and ensure they have a static lifetime and are valid for the entire duration of the program. So here's what the trait descriptor generated by the template actually looks like. Note how it actually has the additional private fields that have been added to the end. And that are used by the implementations of the different methods. These contain the generic parameters that were originally passed as an input to the trait descriptor construction function. And you can see this is used, for example, for the associated type T. This gets turned into a function pointer that just returns the associated type, the type descriptor that was used when the trait descriptor was constructed. And since T has a debug bound on it, this also returns the debug traits impl. Actually, now that I look at this example, it's actually incorrect. Oh no, it is correct. Sorry, because in the previous slide, yes, T has a debug bound, so the T function returns both the type descriptor for T and the debug implementation for T. The constant's just embedded directly, and the method just calls the debug print the same way we've seen other methods work with type descriptors indirectly. So let's recap. I know this has been a lot of deep technical details. To enable a stable ABI, we need to ensure that compiled code in one crate does not depend on private implementation details in another crate. And we've addressed that with several mechanisms: type descriptors, which allow manipulating values whose type is not known at compile time; polymorphic generic functions, which allows a single compiled function to handle any combination of generic parameters; and trait descriptors, which allow polymorphic functions to operate on opaque types which are not known at compile time. Unfortunately, there's some limitations. We can't actually achieve everything. We can achieve the important 95%, but not the remaining 80%. One important one is that generic functions can no longer be converted into function pointers. The issue is that if you call polymorphic generic functions, take additional parameters, so their signature doesn't match the one of the original function anymore, and you can't really get a function point. There's no real way to get a function pointer with the original signature out of that, except maybe do runtime code generation. But we said we wouldn't do that. There's some SIMD intrinsics that use const generics and actually require compile time constants, otherwise LVM seg faults. If these constants instead come from generic parameters which are actually only available at runtime, LVM seg faults. Trait specialization is an unstable feature which allows you to look through, just pierce through the veil of generic types to see what the actual underlying type is. And this is used in the standard library for some specializations for faster code paths for copy types, for example, when a function has a general clone bound. That just doesn't work. And finally, we need to dynamically register type and trait descriptors, which means that it kind of makes the language fundamentally rely on a global allocator being present. Also, since this registration can happen from multiple threads, you also need locking, which again is a complicated topic for people who work in no-stud environments. So we still have some unresolved limitations. And this section is less about limitations, but more about how we can go faster. So we've achieved a stable ABI by essentially throwing many layers of indirection at the problem. This is not great for performance. In some cases, we may prefer to instead allow some leakage of implementation details to regain some of the lost performance. For example, what if we have types who have private fields, but where we know that the layout's really never going to change in the future? This can allow significant optimizations. For example, just moving this type from one memory address to another. If I know the size, I can do it in 2 CPU instructions. Load, store. If I don't know the size, I need to pass it in directly, call memcopy to do a variable size copy, which needs to copy it maybe 1 byte at a time. Just moving a value has become orders of magnitude slower, let alone actually doing anything with this. So we could just introduce an ABI stable attribute on structs, which says, I promise I will never change the layout of the struct. You may assume that it never changes. And now your code is fast again. Another issue is inline functions. So Rust heavily depends on inline functions for performance. The inability to inline a simple function like the map method on iterators could easily just destroy the performance of all Rust programs. And so far, we've been pretty strict about preventing cross-crate inlining. Clearly, the implementation of iterator map is a private implementation detail of the standard library. That should be open to change. However, in practice, really, we're never going to change it. The map just maps. So we may want to say, okay, this is an inline function, and we promise that it's that first of all, it only touches this inline function only touches ABI stable fields, private fields. And secondly, we promise that it's never going to change in practice, so it's fine to inline it. Oh, and this is what I was talking about earlier. If you export an inline function, it can only access private fields that are ABI stable, that are at a known offset. And this is necessary to avoid code that's embedded in downstream depending on non-ABI stable interfaces. So ABI stable can be, you can mark it on the whole struct to say this struct is never going to change, or you can put it on a specific field to say, okay, the struct layout may change, but you can always assume that this field will be available and that it's fine for exported inline functions to actually refer to it directly. So far, we've only talked about preventing private implementation details from leaking across crate boundaries. And this is a necessary step since it allows those private parts to evolve without breaking compatibility. However, it's often you don't want to have a fixed API. You want to add extensions, new features, new methods, new types, etc. And this is something that we want to continue to allow. We want to allow APIs to evolve without breaking API and ABI compatibility. So the cargo book, which is available on the Rust documentation website, has a page on semantic versioning that lists a lot of the various changes that you can make to an API and whether this is a breaking change or not. For example, adding a public item is fine, but removing one is not. You can add a struct field as long as the struct doesn't have all public fields, or it's marked as non-exhaustive, but otherwise the same rules as items apply. You can't modify a public field, but it's fine to modify, you can't modify public fields, but it's fine to modify a private field. Additionally, you can freely reorder fields, etc. Enums are similar. You can add a new variant to, so adding a new variant to an enum is a breaking change unless it's non-exhaustive. Some minor changes are fine, like you can remove the last private field of a struct, turning it into an all public struct, but not the other way around. You can reorder items in a trait. You can relax generic bounds on a trait implementation. You can remove non-exhaustive from a type. Unfortunately, at the ABI level, some of these rules actually change. Reordering items in a trait will break trait descriptors. Changing the generic bounds on a trait implementation will change the arguments passed to the trait descriptor construction function. Removing the last private field of a struct or removing a non-exhaustive attribute actually changes the calling convention for this type, because we need to switch from the standard calling between the standard calling convention where the size is known and the indirect calling convention where the size is not known. So we've tried really hard to keep the rules the same, but we couldn't get it perfectly right. And the best way to actually deal with this, because the rules are quite subtle and can easily be missed, is to use tooling to solve this. It's thankfully very
Good morning, all. Today we have Marco with us, and he'll be discussing, his topic is building a profiler for WebAssembly. Give him a warm welcome.
Thank you. Okay, it works. Alrighty, let's get into it. I'll start the talk with a little anecdote, and then I'll introduce myself. It's a bit weird, but let's do that. So yeah, a short anecdote. Just wanted to kind of like showcase why profilers are important. I mean, I think quite a few people think that they are important tools. But in case you haven't used one or you're not really aware what they do, I just wanted to showcase in what kind of situation they may be useful. I was making some open source contribution to a Rust library, and just like for fun. And it was like a very small change, which I have there at the bottom right. And it was, you know, like I was changing essentially, it was slightly more big than that. Changing some print statements to print just hi and print wrapper of hi, essentially. And you'd expect that this would not have such a big performance impact, but it actually made some of the benchmarks of the open source library was contributing to 50% slower, which was quite a surprise. I didn't, also like one thing that made this slightly harder to figure out was that these print statements were not written in the code, but they were actually generated by some proc macros, essentially. So it was slightly harder to track down, but I didn't know what was going on. Like I was like, okay, this is a very small change. Why would it get 50% slower? And I use a profiler. In this case, I use Samply, which is a native profiler, which is actually really good, and it's also written in Rust, but it's for native code. Love it. And I saw that like there was a big difference in between the profiles of before the change and after the change. And after the change, there were like all these allocations that were happening, and I really couldn't figure out. Like that was a good end though. And then after figuring out that there was an additional allocations happening, then actually I figured out one thing, that the Rust compiler cannot optimize out. Essentially, like the Rust compiler can optimize out the first line. It figures out that hi is essentially a static, and it can just put it in the first string, essentially. But when you wrap hi on with anything, it cannot do that optimization anymore. And the fix was just to get rid of the wrapper in the proc mago generated code when we know that it's a static. So I think, you know, this is a very good example. It was a small change, but I would have not, I'd never guessed that there was an additional allocation happening, because it was also like the compiler, you know, optimizing out something, and it was not doing that anymore. So I really enjoy using profilers, and I do that quite a bit at my day job. So we can talk a little bit about that. I'm a senior engineer at Shopify, and essentially what I work on is Shopify has this templating language that is called Liquid, and it's similar to Jinja or ERB. So it's just a templating language, essentially, and it allows you to define what your storefront looks like. So you can do things like, for every product in your collection, you know, print this HTML to the customer. And what I work on is actually we're trying to take Liquid and compile it into WebAssembly. And it's mostly a performance-sensitive project, so we do spend quite a bit of time trying to figure out where time is spent. And yeah, I have a bunch of interests. You can talk about, you know, with me about compilers, profilers. We also do, I'm also somehow involved with a bunch of distributed systems, because as you can imagine, these storefronts have to be rendered across the world, the closest to the customer as possible. And so it's all part of one big mission to make this fast. And it's both CPU work and I/O and trying to distribute the data around the world. I'm from Sicily, and I love beach volley. Also climbing a little bit and video games, which is, I guess, pretty stereotypical. I built a profiler for WebAssembly, and this is kind of like a talk about what I did, how it works, and what I learned, and some of the things I wish maybe we could do as a community to further improve the state of profiling for WebAssembly. So the reason why I built this profiler specifically was that someone, I think, pointed out that currently we do offer the ability for third-party developers to profile their Liquid code. And this is just uses some instrumentation because Liquid like the previous version, is an interpreter. So you can just add a bunch of instrumentation to the code while it's interpreted to then collect information about how time is spent in your theme when it renders. But now that we compile to WebAssembly, it becomes slightly harder, and I was wondering if there would be an easy way, because we compile to something closer to native, to just use a proper profiler rather than having to instrument the code. And that's why I built this. So following on that, I'm going to try to explain a little bit what a profiler is and usually how it works internally. So there's kind of like two types of profilers. Sampling, which is what I'm going to talk about today, and instrumenting or tracing, which is another kind of compilers. They are also very good, but what they kind of like need you to do is instrument or automatically instrument your code, and they usually have a little bit of overhead because essentially, for example, for every time you enter a function, you need to increase a counter that you've entered that function, and so that you know where time is spent. Sampling profilers don't need you to do that kind of instrumentation, and they're usually considered to be low overhead, and also, it's also like I was trying to make one, and I was just mostly trying to learn, and I could take quite a bit of inspiration from other sampling profilers, like for example, I don't know how to pronounce it, but Prof RS is one that I took quite a lot of inspiration from. And I just built a sampling one. So I'm going to mostly talk about how sampling profilers work today. Cool. So I like to think a bit about sampling profilers, and maybe this is a metaphor that only works for me, but hopefully it works for someone else in this room. But it's a bit like a movie to an extent, and like bear with me with the metaphor. But what a movie is just like a collection of pictures, right? And essentially, if you put them one after the other quickly enough, you get a movie, right? Like you get essentially you can understand movement in that sense and the dynamics of the system, right? A picture on its own is limited, but a movie has additional information because it's an aggregation of them. And sampling profilers are maybe similar, if you allow me to keep on going on this weird analogy. But essentially, you take a snapshot of your program at a certain interval, and essentially, the more snapshots you take, the more precise the information you get out. But if you do it enough times while the program runs, you're going to get a sense of what's happening in the program, right? You know that you were in main, that called foo, that called bar, right, at a certain sample. And then the more samples you take, you may see essentially the functions that appear the most in each sample are usually where you spend time. And so you put together informations from snapshots, and you get profile data out of that. But we'll go back to this with more examples later on. Okay, this is kind of like an introduction to this, but like, can we like how do we actually create one such profiler? So one thing I need to mention here is that the talk is about building a profiler for WebAssembly, but maybe I should have been slightly more specific. But I had to use a specific runtime because WebAssembly has to run somewhere. Like there is no, so far, CPU that actually can take WebAssembly and run it on bare metal, right? And so you have to use one engine that can take your WebAssembly and then actually run it on the machine you have at your disposal, right? And so I used Wasm time. Why? It's like a pretty, I'd say like it's a pretty good engine. It's pretty fast. It's built in Rust, and also it has a few APIs that make building a profiler easier. Also, I work, as I said, at Shopify. We have few people that contribute directly to Wasm time. So if I needed anything, I could just go to them and ask them, how can I do this? Or can we add an API? Or can we slightly change one? And so it was slightly easier because of that too. So that's one thing. Also, Wasm time actually nowadays has its own profiler that it's embedded in Wasm time itself. When I did the work, it was not the case, but now there is one, and that's great. Cool. So as I said before, right, like we want to take these snapshots at every single point in time, whenever, like with enough time in between, because we don't want to stop the program all the time. But we need some way of essentially stopping the program, taking a snapshot, and then making it continue do its thing, right? And so usually when you, like on the left side, I'm not great at drawing or diagramming, but I'll try my best to explain what I'm trying to convey with this slide, essentially. But you have the runtime, which is Wasm time, right? And you give it essentially a program, and when you just use Wasm time, I guess with no flags, no specific configuration, what happens is essentially Wasm time takes your Wasm, it compiles it to assembly, and then it just runs the assembly till it's done. There is no way to get back control to the host or the runtime, essentially. And I guess this is good to an extent. You're gonna, usually in most cases, you want essentially your runtime to just run your code and do it as quickly as possible. So that's kind of what it does. But as I said, we need to have a way to kind of stop the program every so often and take back control, essentially, get out of the program itself and collect some information about the program, right? And so in order to do so, we can use epochs. Epochs are a feature in Wasm time, which allow the code, essentially, what Wasm time does is when it generates the assembly, every so often in the assembly, it adds some instruction to check if an epoch has been reached. And if the epoch has been reached, it gets out of your program and goes back into the host code, essentially, like the code that you've written, essentially. And so you get back control to the runtime, essentially. And this is good because if we get back control, then we can use other Wasm time APIs to get information about the program running, and that's our sample. That's a sampling profiler, essentially. Cool. So we have one mechanism to at least stop the program execution every so often when this epoch is reached, and then we can do whatever we want. We can collect the sample that we need. But how do we, so Wasm time allows you, essentially, it generates code that stops every so often, checks the epochs. But if nothing increases the epoch counter, then the program is just going to run forever, essentially, because the epoch has not reached, so it can just keep on going, and it will never yield back control to the runtime. And this is one very common way to do this, is to use set itimer, which is, I don't know if it's POSIX or Unix, but Linux and Mac OS expose essentially this system call, which essentially you tell your operative system to send a signal every so often, so like some cadence that you specify. And then you can install a signal handler, like what happens when the OS sends you this signal. And one thing that we can do is, okay, now we have something at least that has some sort of like, I guess, stops the program, or like at least sends a signal every so often. So we have what we need to then actually increase the epoch counter. So like what happens is the OS stops the entire program with a signal, and we do something very minimal, which is just increase the epoch counter when this happens. And then when the program restarts, right, after the signal is handled, it's probably inside Wasm, like the Wasm execution, which then is going to check the epoch counter. Now it's been increased, and it stops and yields back control to the runtime. Cool. Also, like after the work, actually, I had to make this work on Windows as well, and for that, I just use a thread, which is better than nothing. So I have another thread that just sends, essentially increases the epoch counter every so often. So that's one thing. And then what do? We use actually, like Wasm time already allows you when you are in when you're handling an epoch, or really like when you're handling any call from Wasm into the host, like the runtime itself, it allows you to capture a stack trace. So that was one of those APIs together with epoch handling that was nice to have in Wasm time that would make it easy to build such a profiler. And so what we do is we ask Wasm time, okay, what's the current stack trace or back trace, call stack, whatever, like there's like multiple names for these things, but essentially, what are the functions that are currently active on the stack for the Wasm program? And essentially, Wasm time is gonna give us back something like, your, like it's main, foo, bar, bus, right? Like the stack, the call stack, backtrace, whatever you wanna call it. And so every time we do that, like every time we get an epoch interruption, we capture one such sample. And if we do it fast enough and enough times, essentially we've built enough information to have profiling data that then we can feed a UI to then display flame graphs or other kind of profiling visualizations. And to be clear, I did not build one such UI because there is like enough there that you can just use if you give them something like a file with the information about the program and the profile data. And what the profile data kind of looks like is this. So you have frames, which is all the functions you've ever seen. Essentially, like like main, foo, bar, all the functions of your program are like, it's almost like a set, essentially. And it's all the functions that have ever been seen in all the samples you've taken. So such that we don't duplicate those names in all the samples, essentially. And then you have samples, which is a vector of usize. And so this is a bit of an indirection, but essentially the usize is just indexed into the frames so that the names are not duplicated, right? Like you don't want to have main in the samples like, I don't know, 1,000,000 times. That's like a waste of space, essentially. And so you can kind of optimize this out with, you have frames that are all the unique names, and then samples, which is just a vector of vectors of function names. So the inside vector is just one sample, essentially. It's like all the function names in that sample, and then the outside vector is just all the samples you've taken. And then you can have weights, which is an optional of of a vector of U128. And so like each sample can have its own weight, essentially, like how important it was. Usually you use time as the weight, essentially the time that has elapsed since the last sample you've taken. That's the importance of that specific sample. But you can use also other metrics, actually. And one that was actually quite useful because this ended up being used to an extent inside Shopify because we offer some sort of like function as a service system where you can customize some of the behavior of your storefront, for example, your checkout or your cart, maybe like delivery options and all of that. And we do this through essentially third-party developers can submit WebAssembly functions to us, but one limitation that we impose is that these WebAssembly functions cannot exceed a certain computational budget, and this is done through Wasm time. Wasm times allows you to essentially limit the amount of computations that one invocation to a WebAssembly program can do, and this is through Fuel. It's another API that comes from Wasm time, but essentially you can think of it as anytime you do any operation, you burn some fuel. And when you've burned all the fuel that you were given, the execution stops. And that's it, like you cannot compute farther than that. And this is so that, we don't want people to write functions that increase the checkout time by like 10 seconds. That would be insane and also probably decrease conversions for us and our customers. And so we have a very strong limit on how much computations you can do on these functions, and this is Fuel. And so one thing that we ended up adding to this profiler is not only we can weight these samples by time, but we can also weight it by this fuel that has been consumed since the last sample has been taken. And that turned out to be quite useful even internally because it helped people kind of figure out where they were spending their fuel. And this is a little bit of looking ahead. And it's mostly just like dreams or wishes or hopes I have for maybe better profilers for the future. And there's like mainly two topics that I kind of care about that I wish I could see happen in the future. And so it's two things. One is supporting languages runtimes profiling inside of WebAssembly. And the other one is more easily allow new languages, like entirely new languages, that are built on top of WebAssembly to essentially emit enough information such that profilers can actually understand the semantics of the language, not of the assembly that they produce. And so I'm going to go into more details on each of them. So the first thing is, right, you can compile your Rust or your C to WebAssembly. And if you run one profiler like mine or even the one that is now included in Wasm time, you would see enough information to figure out essentially what's happening in your program, because these are languages that are compiled to native code, and native code here is WebAssembly. And so if you're calling the Rust function food, you would see it in your, maybe it's mangled, but you can unmangle that, demangle that. You would see it in your profiles, like in your samples, essentially. But WebAssembly is a very large boat, essentially. And there is like use cases where you may want to run your JavaScript or your Ruby or your Python inside of WebAssembly runtimes. Maybe because you want to run them in the browser for whatever reason that is, or you want to offer again something similar to what we do right at Shopify, where we allow people to write their own customizations, and sometimes they don't want to write. These third-party developers don't want to write Rust or C because they're used to writing JavaScript or Ruby. and so you're gonna have to make the mapping. And you can run, Ruby and JavaScript and Python in WebAssembly, so there is no particular issue there. But if you try to profile them using a profiler that works with WebAssembly, like the Wasm time one or the one I wrote, you wouldn't get any information out of that, because it's something similar to when you try to profile, a Ruby program using perf or a native profiler, right? You would only see, oh yeah, you're using the Ruby VM, because that's the C code that actually runs on your machine, but you don't actually understand like what Ruby code is the VM running. Who knows, right? Like there is no information there. And so like there may be like a solution here, especially because it's a fairly new platform, WebAssembly, and there is ways to define, we have ways to define interfaces like WASI, and with components, it's going to be even easier, right? Maybe we could define a shared interface that all of these runtimes can expose to essentially inform the profiler, oh yeah, like, okay, yes, that C code or Rust code is running that powers the VM itself, but also like at this specific point in time, this Ruby code or this JavaScript code was actually running inside the VM. And with that, we could collect both samples and maybe even interleave them with some heuristics or whatever, just keep them separate, but at least you can put them on a time, like on a time graph together and figure out what's happening maybe. But at least we have information about what's happening inside. So that's one thing that I wish actually existed. The other thing is, and this maybe it's just because, as I said, like this is kind of like what I do. So we are writing a compiler for Liquid. And Liquid is our own language, right? It's a simple language. It's a templating language. It's not doesn't have that much, semantics or complexity. But we compile it to WebAssembly itself. And sure, we could have used LLVM to do that, but it felt like a bit of a overkill to compile a templating language to WebAssembly to use LLVM. Also, ideally, we want to run this possibly during a request, so running all of LLVM may take a little bit of time, and it may essentially it may not be worth it. And so the other side of this is, so you don't want to use LLVM. You can use a bunch of Wasm code generators that are like very fast, and they exist in Rust and also other languages, right? The issue there is though that none of these, as far as I know, and maybe this has changed or I haven't looked too hard. Essentially, they don't emit any kind of debug information like dwarf for your WebAssembly, right? Like, so I'm compiling Liquid in my case, right, to WebAssembly. Now I have this WebAssembly, I run it in an engine, and I can profile it, but then I kind of like can only see that, yes, like the code I compiled is, this, but it's like trying to profile JavaScript without source maps or trying to profile Rust without dwarf information, right? Like you can see the assembly that it's running, but you need to be really understand your own code and really be good at essentially reverse engineering to figure out then what's happening if you don't know why that code was emitted, essentially. And so, do I have another slide now? Yeah, so like kind of like the solution here, which I have a prototype, but it's not finished, essentially. It would be neat to have a fairly like lightweight library that allows you to generate WebAssembly, but at the same time also annotated with dwarf information. Because this is, like oftentimes, essentially, at least for this kind of like my use case, right, like it's a simple language, we're not doing too many optimizations, and ideally we just want to be able to emit WebAssembly as fast as possible, and if needed, also add dwarf information and debug information so that the profiler can then, return, yeah, you spend time in this specific line of code in your source code, not in the emitted code. And yeah, so I guess that's another thing that we need to see happening. And with that, I've finished my talk, which I guess is a bit early, but I guess it's more time to get refreshments and also questions.
Thank you very much. So, does anybody have any questions?
Yeah, you're just talking about annotating your Wasm with dwarf information.
Yeah.
Could this be something like, in a native language, I would expect to have like a debug symbols file, or in like TypeScript, I'd have like a mapping file to get back to JavaScript. Is there a solution like that where we don't have to change the Wasm we generate, but we can just generate a companion file that solves the problem?
So essentially, like, as far as I understand, there is one such format that already exists for WebAssembly, which is somehow standardized, which is dwarf. And it's not the entirety of dwarf. It's actually like a subset, essentially, for WebAssembly. And I think you may be able to generate it separately, too. But I'm not sure all engines are able to load the dwarf information separately from the WebAssembly itself. But like that is something that can be added to the engine. It's not a limitation of WebAssembly itself. But yeah.
Awesome presentation.
Thank you.
One question, so can follow up on the dwarf information. Is why dwarf? Is that just because it's supported, or does it allow visualizations? Like, how would you then visualize that with the rest of the profile?
Essentially, it has essentially, like, what it allows to do is the engines can read the information, and when you ask for the stack trace or back trace, they also tell you what was the source code that essentially corresponded to the specific function in WebAssembly. And it's also useful for debug, like if you're trying to run a debugger for WebAssembly, they would use the same information essentially. And why dwarf? I don't know. It's kind of like what it's been somehow standardized around WebAssembly for this kind of information about source to WebAssembly information. But yeah, it just has enough information to know, okay, given this WebAssembly, what was the source code that, was the cause of that? Yeah.
Thank you for the talk.
Yeah,
it's very interesting. Have you, I guess all of this works either with custom imports from your WebAssembly module or with WASI Preview 1. Do you know if it would be possible to do this with a component model and Preview 2?
You don't need neither. Like, essentially, it should be agnostic to WASI. Like, it doesn't use WASI, or it doesn't use components or anything. I'm not sure what implied that you may use components, so like if you can clarify that.
Yeah, I know that, for instance, you can run a debugger with Wasm time to debug your WebAssembly code using dwarf information, but that kind of breaks when you start running components because of how Wasm time generates the native code.
Right. Yeah, it may just be like because components are maybe not stable enough yet. As far as I know, I mean they're like they're still being worked on, and I'm not too sure why they would break. So maybe that's one reason, but maybe it's already been fixed. So I don't know too much about the state of the current implementation of components and how they interact with dwarf. But yeah, something to look into, I guess. Thank you.
Yeah.
Nice talk. I hope this isn't too basic a question, but I was kind of curious why you'd want to profile WebAssembly in the first place, because isn't the point that it's like super performant? So I guess at least in the kind of front end cases, I've only really seen people use WebAssembly when they want like, way better than JavaScript kind of performance. So I'm curious, is it to kind of really make sure you optimize that, or are there kind of gotchas with WebAssembly where you might have, missed something really obvious that the profiler will help you with?
Yeah, so like, I mean, it is more performant than JavaScript in certain cases for the browser. But it is still the case that you may want to look into if you're doing anything particularly dumb or why is your code slow. Like, you may still hit that use case. And actually why I wrote this in the first place was again, like as I said, like we're trying to compile Liquid to WebAssembly, and one feature that we provide third-party developer is a Liquid profiler to figure out why their storefront may be slow or fast. Essentially, figure out where in rendering their web page, their code is slow. And now that we compiled them to WebAssembly, like that profiler mostly instrumented the interpreter that we were using to interpret Liquid. But now that we compile, we haven't finished this. Like we don't actually offer a profiler for Liquid compiled to WebAssembly yet. But this is a first stepping stone. And once we figure out also dwarf information, then we can put these two together and offer the same kind of capability for third-party developer to figure out why their Liquid may or may not be fast, essentially. Yeah.
Yeah. You mentioned in your talk that Wasm time ended up with a sampling profiler anyway. Like, how many of the other runtimes, like how good is support for sampling profiling? Like, can I, if I've got like a browser module, like is it likely that I'll be able to already profile that, or is it, I'm a little bit out of the game on this. So.
Yeah, so I'm not too sure how many other engines support essentially profiling your WebAssembly. I would be surprised that if Wasm time was the only one, because it shouldn't be too involved to ship. But yeah, I don't know essentially like what other engines and what's the support for this specific feature out there. Yeah, sorry, I guess.
So what about async support? Because you can compile async code to WebAssembly, but even with dwarf information, it's not easy to find out what called what, because there's always the indirection through the runtime. So many runtimes allow to put additional information in your code, but there's no standardized way to get that, especially when then compiling that code to WebAssembly. So could you envision an extension to deal with that?
So wait, what was the language? Sorry, I didn't get.
So you can just use Rust, but
right.
Async Rust. So you have an async.
Oh, async, right? Like yeah.
So that's compiled to state machines. Those that can get polled every now and then by the runtime. And
essentially, I don't know if there is any thing that we can do with WebAssembly itself to make it easier. I've looked into the async profiling, is like I guess like how you do it just for native, and it seems like slightly complicated. But yeah, I think I don't know. Like I've spent some time trying to think about it for native because it's something that we are gonna like do, and it would be neat if we could profile continuously in production as well, like all the Rust code that we have. I don't know, like I think there may be something around like maybe like trying to marry some profiling with tracing essentially, and then it's mostly like an aggregation problem afterwards essentially to then only show, because like one thing that is very nice that we do at least for Ruby, which is not, at least our Ruby is not async for now, but it may be soon, so like we'll have the same problem there. Is that we have a per request profiling. Essentially, we can get a profile for a single request, but once you have async in the mix, like what's a request? Like like you don't have a start and end that it's very, and ideally you want to handle multiple requests at the same time while they do their I/O, right? Like you don't want to, like we are blocking right now, so it's easy, yeah, like there may be some solution there with tracing essentially, like such that afterwards you can figure out essentially what happened during a request through some additional tagging and but yeah, I guess I don't know if WebAssembly can help particularly to fix it. It feels like it's a more generic issue maybe, but maybe WebAssembly, I don't know. I haven't thought too much about the two together. But yeah, cool. Yeah, good question.
Any more questions? No?
Okay, thank you everyone. We can leave early for refreshments. One last round of applause for our speaker.
Is it good? Sweet.
Good afternoon, all. Welcome back. We have a brilliant talk by a brilliant man, David Haig, and his talk is an open source hearing aid in Rust.
Yes. All right. Thank you all for coming. I know you had many options today, and I'm pleased to see so many of you here. I'm going to be talking about an open source hearing aid in Rust, something I've been working on for about a year and a half. Right, where did I get this idea, or why did I decide to actually do this in the first place? My background is not in electrical engineering or embedded Rust or anything like that. I come from a finance background. I've spent the last 15 years working at investment banks, building pricing and financial modeling and stuff like that. So this is a far cry from sort of my background, but I've always been interested in electronics, in Arduino and stuff like that. And in fact, I got into the embedded space through the Arduino ecosystem. And I brought some props today. This is the first thing I ever made. This is like what I used to do. This is about 6 years ago or so. This is like an STM32 blue pill, and it's sort of cobbled together, and it's all wired up like this, and you put it on a breadboard. And this is kind of how I started my journey. And then I got into Rust in order to learn how to maybe make embedded software a little bit more professionally. I was introduced to Rust through and kind of Bluetooth at the same time, and I discovered over the pandemic I started working on this thing called the LC3 codec, which is a Bluetooth audio codec. I kind of stumbled upon the spec when I was looking for stuff to do over the pandemic, and I looked at it and I thought, I don't understand anything there, but I'll give it a shot and see if I can implement the spec. And this is all about sort of audio compression for it's called low complexity audio compression. So it's for embedded devices. So this took me about a year to implement this thing because I didn't know what I was doing. it's kind of very similar to this project. You know, no idea how to build a hearing aid in the first place. But this gave me confidence, and I figured I need to actually use this codec for something. I want to build something physical. You know, those are the things that I built before. I want to build something, I want to learn how to do PCB design. So that's kind of how I started in this whole area. Right, but before I start, I just want to explain what a hearing aid is. It's actually a very broad topic. A lot of people don't really know what a hearing aid is in general. So I asked our AI overlords to generate me an image of a hearing aid to show you guys, and it generated this creepy image over here. And it turns out it didn't know what a hearing aid was either, just that old people are supposed to wear them. Of course, that's not what a hearing aid really is, and hearing aids are meant to be worn by people from all walks of life. Part of what I'm excited about with this project is I want to bring hearing aids to a younger generation, and I want to make them less taboo to wear. So at its heart, hearing aid is essentially a microphone, some sort of form of amplification, and a speaker. So really simple, but it's all in the amplifier. What are you doing behind the scenes? And this is the kind of hearing aid that I'm going to be making over here. So this is called a receiver in the canal. And that thing over there is a little speaker that goes inside your canal. And then the sort of the rest of the hardware goes behind your ear. So battery, processor, microphone. Sometimes the microphone's in the ear, but that's actually quite rare for these kinds of hearing aids. So microphone's behind the ear. They're very discreet. They're often like the same color as your hair. And yeah, that's what I'm going to make. So while I was making this thing, I thought, you know, this is not the only kind of hearing aid. You get behind the ear, which is like a tube. There's these big ones that you see. There's in the ear, which is kind of like molded to your ear. There's in the canal and invisible in the canal. And these are hearing aids that go right inside your canal, and you can't even see them. And those are, you know, sort of way beyond my capabilities. I thought this is something that I can reasonably kind of make physically. And then there's body-worn hearing aids. So this idea to build an open source hearing aid is not a novel idea. There's a very popular project called Tympan, which I drew lots of inspiration from. It's quite a mature project. They use Arduino, and the hardware is actually quite. The hardware is so fast that they can run a lot. They can get away with doing lots of software-defined filters and stuff like that. So that's a really good project to look at if you're interested in the software-defined filtering and stuff like that. So anyway, I thought, well, what makes up a hearing aid, and at the bare minimum, what do I need to build in order to create something that's going to be, you know, reasonable to wear. Of course, when you look online at what a hearing aid does, you're just swamped by so much marketing material. It's hard to actually know at a technical level what it's really doing. So anyway, after lots of research, I kind of decided that if I implement these following 3 things, then at least I would have something like reasonable. Anyway, the first one, I'm sure you've all seen, is a graphics equalizer. This is something that breaks the frequency bands up, and then we've all done this. You know, you make certain frequencies louder, and typically when you go to an audiologist, they will build you a little profile so that your hearing aid will change the frequency response. So that's easy. I can do that. I did very similar things with the LC3 codec. Then the next one was, this is a technology that I was very excited to learn about and to delve into. And this is the idea of audio compression. And this is not to be confused with like MP3 compression or zip file compression. This is what's called reducing the dynamic range of the audio. So this is very common in the music industry to make the singing voice more clear, to understand what people are saying, and it also has uses in hearing aids. So this is actually a sort of a very simplified form of compression, but essentially at its heart, what compression does is it makes loud sounds quieter, and so that you can generally increase the volume of everything. So you can imagine a sound wave that's sort of bouncing all over the place. It's got huge peaks and troughs. You want to reduce the dynamic range and have everything in the same sort of energy band, and that's what compression really is. So here you can see this detects an attack, and then it sort of attenuates that, and it kind of brings it down. In hearing aids, it's a little bit more sophisticated than that. So you don't have a sound producer to sit there and vary the levels. You have to do that automatically. So if you're in a quiet room talking to people, it must generally bring up the sound, and if you're in a noisy environment, it must bring things down. And so it's just moving all the time on top of this whole attack release type stuff. And then another thing is noise gating technology, and that's if you're going to generally make things louder, then you're going to have hiss, microphone hiss, and all that sort of stuff. So you want to have sort of a noise. You want to get rid of that as well. And then the final thing that I needed to get working was ambient noise cancellation, and this is very critical to a hearing aid. This allows you to essentially a hearing aid. These particular hearing aids are they're very comfortable to wear. You can they're designed to be worn all day. They're invisible, but because of that, they don't push against your ear canal. They're ported. They breathe, and but they also let through sound. So you've got to subtract that audio through noise cancellation. And the other benefit of noise cancellation is it buys you time for adding latency to your audio pipeline. So you can imagine if you are taking a long time to process something, you would hear the processed audio as an echo because it would reach you at a later stage. So this is really exciting for me because this means that, stretched to its limits, you could possibly negate what somebody is saying and maybe even process the audio on a phone. Maybe you could do language translation, stuff like that. So this has got great potential, and I really need that. Okay. So without further ado, this is the device. I designed and got that thing made, and this whole talk is going to be about that process. And I happen to be wearing them, but it might be difficult to take them out because I've got this contraption on my head. But so hopefully you didn't notice that I was wearing them, and that was the whole point. But yeah, this is them over here, and that, yeah, you're not supposed to see it, and it's a very comfortable thing to wear. Didn't block my ears, which is why I could talk to you guys, which is really important as well. When you're wearing earphones, it's one of those things that's, it's a very antisocial thing to wear, but a hearing aid is a social thing. Okay, so there are a couple of things on this board. There are actually 61 components on this board. I won't go through all of them, but I'll discuss the ones that are most sort of interesting from a developer point of view. So you've got a microcontroller here and some other chips that I'll discuss later. This is the main chip that I've written software for. This is a dual-core microcontroller from Nordic. And I've got quite a lot of experience with working with this chip. It's quite a modern ARM Cortex M33. It runs at, one of the clocks runs at 128 megahertz. So one of the CPUs runs at that and the other one runs at 64. It's got a built-in Bluetooth radio, which is great, and it supports Bluetooth 5.3, I guess that's the latest version, or 5.4 maybe. But yeah, Nordic kind of leads the way in Bluetooth technology. So this uses Bluetooth Low Energy, which is great compared to Bluetooth Classic, which is not really feasible for hearing aids because it takes too much power. But Bluetooth Low Energy does work for hearing aids. Okay, so it wasn't enough for me to. My initial design, all I had was this chip, and then whatever I needed to power it. And this thing does a lot. You can do lots of software-defined filters on it, but you also need to sort of interact with the physical world, and you need to send audio. You need a thing called a digital to analog converter, and then an amplifier. And I couldn't find miniature versions of these things, and I tried to design my own. It was actually a real struggle, and I nearly put down the project as a result. I learned a lot about amplification and all that stuff, but at the end of the day, I realized that I didn't have the electronics skills to build something and be confident that I could make a low noise amplifier. So I really needed to find components that worked already, and not by chance, I discovered this DSP chip here by a company called Cirrus Logic. And I found it because I bought an audio dev kit from Nordic. And this is like, I've got a whole drawer full of dev kits. And this has been my sort of portal into this whole field. I rely on them to learn how the manufacturer wants you to use the chips and stuff. So a dev kit will come with schematics so that you can kind of see how you're supposed to power things and all that. So when I was looking through the schematic, I found that this little chip over there, you can hardly see it here. It's like a tiny little blip. That thing is, that's exactly what I want. It's got a amplifier, and it's got a digital to analog converter, but it's so much more. And it's got a whole bunch of hardware accelerated stuff. This is just a few things that it can do, like multiply, accumulate, fast Fourier transforms, least mean squared, finite impulse response. These are things that, is a maths toolbox for doing audio compression or audio filters and stuff like that. Very, very, very useful. And then the last thing was battery charging. So this thing runs on a lithium-ion battery, and I had to find a way. That needs to be charged. I didn't want to use disposable batteries. The weird thing is, this is the simplest part of the whole system, but it's the only part that I didn't quite get right. And I can power the thing off batteries, and I can power it off USB, but the charging chip won't charge my battery for some reason. So it wasn't entirely a success, this whole thing. There's definitely more revisions to come out. But yeah, it was quite an emotional moment when these things arrived in February, and I plugged them in. They worked. They sat on my desk for a week. I just sat looking at them, and I was too scared to plug them in. Anyway, okay. So this talk is about this whole conference is about Rust. So I'm going to talk a little bit about embedded Rust and why on earth I would choose to make, when there's so much literature and there's so much stuff in C and C++, why would I build this in Rust? And yeah, your answer's over there. It's a safe language, and especially for memory safety, when you're dealing with audio, a large part of your memory is an audio buffer. So it's quite easy for, if you have memory problems or like a corrupted stack, for it to also corrupt your audio buffer. And hearing aids have pretty potent amplifiers on them, and you could actually do hearing damage. So here's like a safe language for a safe medical device. And just a little sort of segue here about ear damage. So people think that I'm a little bit crazy to be building a medical device, and I don't really, how can I do this? I'm going to damage my ears. But actually, this little speaker thing here, this is an off-the-shelf component. This is like regarded as a consumable in the medical aid industry. People break these little wires all the time because you're manhandling them. So I basically chose this one because it fit. I could connect it to a board really easily. But I didn't know the tech specs for it because they don't, it's all marketing mumbo jumbo. They don't ever give you that sort of information. So I kind of ordered a couple of these things, and by happy coincidence, the first one that I ordered was did not impedance. It had a poor impedance match to my amplifier, which means that the energy from the amplifier kind of gets reflected when it hits the receiver. Now this is not what you want, obviously, in a device, but it also meant that if there was any mistakes in my code, or maybe there was some feedback or something like that, I wasn't going to blow my eardrums. So I've used this thing for my development, and then I have found RICs, wires that are impedance matched correctly. So yeah, that's a little sidetrack anecdote. Okay, so I decided to use a real-time operating system for this project, and I chose Embassy. And I've got experience with, I've used Embassy for quite a few years now, and it just keeps getting better and better. It's on stable Rust now. Embassy stands for async, embedded async, and it's just a runtime like Tokyo, but it's built for async. And this is regarded as a real-time operating system because it allows you to, it's got, and it's hardware accelerated. So the wakers are essentially connected to interrupts. So if you await something and you've set things up correctly, then your microcontroller actually can go to sleep for months at a time. So imagine a PC that can actually just sort of shut down when you await. It's like an amazing thing. And that's what you get when you're using Embassy. Of course, you have to do certain things the right way in order to achieve that. And I work with a power profiler, and I try out different things, and I see how much it's going to use, how much power each thing uses. So I'm just going to show you a little bit of example code that I wrote for this audio dev kit. So another thing was, once I started using this dev kit, this is great because I could start designing the program, and then I could also do the hardware at the same time. But I wrote it so that it could run on this thing and on the hearing aid. So this is a little program for this device, and this has got buttons and things, which is great. And all this little demo program does is, this is the play loop. This is running at 48 kilohertz, right? So this little loop is whistling around at, sub-millisecond latency here. And what this thing is doing is, if you happen to be pushing down, if it's in play state and you happen to be pushing down the tone button, it's going to fill the output buffer with samples from the waveform generator. If not, it's going to fill the output buffer with samples from the microphone. If I had to use callbacks and stuff like that, say I was using Arctic, a different, RTOS, I would have to somehow get this waveform generator onto that interrupt handler, and it would be maybe a little bit nasty. So this is a really easy way to sort of work with, this is how I would build stuff at a higher level. And this is why something like Embassy excites me so much, because it's so easy to do this stuff, and it's so readable. Here, this is the await point over here, and this is because this is the full. Over here, at this point in time, we have the opportunity to run some software filters, so we can, do an FIR filter or whatever. And this is actually when I was experimenting with software filters, I would put all the logic here. I would do it all here. And because we're only dealing with 32 samples at a time, we have 650 microseconds of time to do our filter. It's not a lot of time, but we've only got 32 samples to work with. And then of course you could increase the number of samples, and then you get higher latency. So you want to keep your latency as low as possible. Otherwise you get echoes, and then active noise cancellation becomes a thing. Anyway, this send and receive is essentially, it's instructing the microprocessor, the microcontroller. It says, I've put the data in the right buffers. You can go to sleep now and turn on a DMA, direct memory access peripheral that essentially streams the audio to the peripheral. So that's been set up before, and if I look at the power profiler, the power drops, by 1,000 times while it's doing this, because it's done its high computation stuff, and now it's just sitting there streaming the data. And then if you happen to be in play state, I just wanted to show you this thing over here, and this is me using a bounded async channel of length 1. So this is regarded as quite a high-level thing to use on an embedded system, and the fact that you can even use async channels is amazing to me. So that's like a turnstile, and that just sits there and gates the thing so that it just waits until another async task pushes the button. So obviously there are more tasks running on this thing that are off screen. Okay, a little bit about writing drivers. So the manufacturer of this DSP chip already supplied a driver, so why would I write the driver in Rust and do all that work again? But writing a driver is not actually such an intimidating thing. It's not a very complicated thing. I think when people think about writing drivers, they think of how difficult they are to write for operating systems like Windows and Linux and stuff. But writing drivers for embedded software is actually very straightforward. At the basic level, all you're really doing is you writing values to registers. And in this case, it's a 32-bit register, and there are a whole bunch of settings inside the register that essentially make up, they have side effects. So you write to this thing, and then there's a side effect of doing something. Right. So here's an example. Oh yes. When I was looking at the C libraries for this driver, typically it's like a large header file and listing all the registers, and then sort of a whole bunch of bit masks and bit shifting information. And once you know how it all works, it's kind of easy to use, but it doesn't actually get used that way. And even the sample code from the manufacturer didn't use their driver properly. I would see lots of hard-coded register values, and I say the manufacturer. These are example projects built by other teams. I don't want to blame anyone here, but I saw lots of sort of code duplication and sort of opaque things. So you'd write this register value, and then somewhere else in the code would write to the same register, but it was slightly different. And this is really difficult from a developer's point of view, because it's really hard to figure out what's going on, and you have to sometimes reverse engineer things, and I just didn't like that. And I thought there must be a better way to do this. And so this is kind of how you. I also wanted to make it so that you could still hard code things, and give people the benefit of the doubt. Maybe they're hard coding register values for performance reasons. You can pre-calculate it. Why do you have to calculate it on the fly? So here, I wanted to make it so that you could hard code things, but you didn't have to. You could still read the code. So here, I'm using something that's fairly recently stabilized in Rust, const expression, right? And this thing, this whole thing is a const function, which means that it gets evaluated at compile time. So this essentially just turns into a hard-coded two-dimensional array, which you can just blast down the line, SPI bus. So here's an example of an awesome example of zero-cost Rust at work, where you can actually see what you can. I'm forcing people to choose specific enums. There's no way to put invalid data in here, so you can't put. It's really hard to mess this up, and anyone can look at this and understand what's going on. So here's a little excerpt from the data sheet, and this is a typical register. This is the dynamic range control. This is one of the control registers, and as you can see, this is jam-packed with lots of settings here. you can set the gain and thresholds and detection modes and quick release and all sorts of weird things. And here, this is the actual implementation of that information there. So it's not a lot of code. There's nothing fancy here. There's no macros. There's no unsafe Rust. And this is how you can write embedded software. In fact, there's no unsafe Rust in any of this code at all. Not that unsafe Rust is bad, but I just didn't need it because we're at the level now in Rust, in the Rust project, where these awesome tools are available to us. There's a little funny thing here where I'm allowing a U8 to be passed in, but I have to truncate it to 5 bits. So it would be nice for me to control that a little bit better. But yeah, at least you can't put invalid data in here. And the idea with these drivers is you're never really going to use a driver by itself. You're always going to reference the data sheet. You can build something on top of the driver so that you don't need to even look at the data sheet. But at this level, I wanted to make something that somebody could pair with the data sheet. And that's what this is. Right, that's the end of the Rust. I'm going to talk a little bit about how I went about building this thing. All the stuff is available on the repository, by the way. So you don't need to, yeah. I specifically made this quite small because I just wanted to show you a brief sort of idea about how simple the circuit really is, and all that. So I used this EDM tool called KiCad, and I specifically use that because it's a free to use. It's open source. I could have used LTM Designer because they do have, free options for open source projects. But I kind of wanted something that was totally open source and free to use with no caveats. And then I also want to mention this YouTube channel here, Fool's Lab. I use so many resources online. I watch so many videos, and I'm indebted to so many people that just put their stuff up online. But I specifically wanted to sort of highlight this particular one because it was so sort of important for this task over here, and learning how to lay out a PCB, how to do the circuits, what things are important, what things aren't important, and all that sort of stuff. And he's got like a whole series of stuff. If you ever want to build your own PCB, then yeah, highly recommend that you look at that. Right. So just a little bit about how this works. There are actually 3 sheets on here. So this is a very simple circuit, a schematic. It's only like 4 pages, whereas this thing's got 30 pages, and this is a real beast. And that's 30 pages isn't even that hardcore. Some things are 100 pages, 200 pages. So you get this is very straightforward. Because, and to me, it's kind of like Lego. I'm just connecting this microchip to that microchip using those wires. And you don't really need to have a very strong knowledge of electrical engineering to do this sort of stuff. You look at the data sheet and it tells you how see all these capacitors and stuff here. These are essentially like local energy storage for power pins and stuff like that. And this is stuff that you learn when you're essentially building this stuff. And yeah, it was just a big learning process going through all this stuff. This is once you've done the circuits, you start building you start routing it out like this. And there's certain techniques to that. And there's just a whole lot of stuff that I had to learn to do that. Okay, then getting it manufactured. So this is something that you don't learn when you're doing research, because this is an experience thing. So I'm quite excited to explain to you guys the thing that I went. When you watch these YouTubers, they're all sort of telling you these manufacturers are great because they're being sponsored by them, but nobody really tells you how the process actually goes. So I did lots of research, and I chose one of these 2 manufacturers, PCBware. If you've ever, these will be very familiar if you've ever looked into the space, JLC PCB or PCBware. These are based in China. And I won't say which one I actually ended up going with, because my experience was probably had a lot to do with how naive I was, and there were I wouldn't be surprised if there's some serious technical problems with my design. So you know, it would be unfair to say, oh, it didn't work because the manufacturer messed up. So just take the next few things with a grain of salt. So these guys were, both of them, I had dealings with both companies. They're extremely friendly. You have this sort of imposter syndrome when you're getting your first, this is my first PCB, by the way, to make. And you get this sort of imposter syndrome where you feel like you're wasting people's time if you don't really know what you're doing. And especially if you submit a design that you've never done before. But all the correspondence was so slick and so friendly, and the engineers got back to me, and the salespeople got back to me. In fact, it was so good that, and the English, the written English was so good that I actually assumed that I was speaking to a native English speaker, when in fact it was just a really good translation algorithm. So if I would, and quite a few things got lost in translation, which caused delays. So I would say something, and then they would get a completely different thing, and it was because of the translation. So there's a little trick I use now. I write stuff in English, and then I convert it to Mandarin, and then I convert the Mandarin back to English, and then I read the two English versions, and if they kind of make sense, then at least I know, I'm not going to have fundamental problems there. So this is regarded as an advanced PCB. So this actually cost me quite a lot to make, about $1,100 to make 6 boards. They're tiny. So I was quite scared, submitting this thing, and I stared at this stuff for ages, and eventually I just pushed the button. I said, I'm just going to get it done. And if it blows up when I plug it in, so be it. But even that, the engineers did spot. They widened some of my tracks, and they fixed a few things for me. These guys X-ray things. This uses BGA parts, so ball grid array, and specifically the DSP chip. It's a 0.4 millimeter pitch pin, and the pins go throughout the whole chip, so you can't kind of root them out. So I needed to do what's called via in pad, so a hole in the pad. And this just increases the price of your stuff. So anyway, so not all these things worked. I had 6 made. I've kept one in its original packaging because I'm sentimental. And then these ones, I've got 2 that work. And these ones over here, this particular one was like a dead short, and I was missing a capacitor. This one, I couldn't communicate with the DSP chip at all, so it just didn't respond. So you kind of send a hello when you're communicating with these things, and this thing just didn't respond. This thing, it worked until I put it on my head, and my head started heating up the device, and then it started crackling. And then I figured out that it was just a dodgy solder joint, because when I push the chip down, it works. So definitely problems here. But I don't know if it's how I routed it or whether it really is a manufacturing defect. So that's why I said it's unfair to blame the manufacturer. But I think as this project goes, I'll speak to proper electrical engineers, and they'll tell me. I'm sure they'll tell me what I did wrong. Okay, so that wasn't it. I still had to put this thing in an enclosure, right? And I had to learn how to make a 3D model and a parametric model. So parametric means that you can change various like angles and values, and you can elongate your model and stuff like that, so that I could experiment with different configurations. So that's kind of what it looks like over there. I used FreeCAD. I could have used an easier to use tool. This is actually an amazing tool once you get to learn it. It crashed a few times on me. And then like the other one, this Mango Jelly was a great resource to use. I learned so much from this chap. Here's my hearing aid kind of on the surgeon's table. I've got a little a debug cable plugged into it there, so that's how I program it. There's the battery. It's a 40 milliamp hour battery. And then I've actually got off screen, I've got a power profiler on there. So I can actually see how much power I'm using. Then this is I actually originally set up, this is my 3D printer. I originally set up this in my office, but I moved it to an emergency workshop that I made in my spare toilet. So yeah, this hearing aid was made in the toilet, basically. Yeah, this is a resin printer, and here's my sort of graveyard of past attempts. But it's the detail you get from these resin printers these days. This wasn't an expensive setup. It was about £500, and then I bought a little microscope there. But it wasn't a very expensive setup. So this is an accessible hobby, and you kind of have to have this setup. You can't really get a manufacturer to print these things for you, especially when you're iterating. So I might get a manufacturer to, once I have a solid design, maybe make something that's a bit more robust. But this resin is called nylon lac, and it's very tough. So I haven't had any durability problems with it. Okay, second last slide. So what are my plans for this project? First starters, I want to do sort of on the fly filtering. I want to be able to remotely control this hearing aid. So have like a command and control type setup, and be able to program it remotely as well. I want to have like an open API for Bluetooth so that you can do control and logging. I want this thing to be used for research, but also for play. So I want people to buy this thing and maybe not even use it for a hearing aid. Maybe you can use it for, think about what a hearing aid really is. It's a socially acceptable thing to wear. It's not socially acceptable for you to sit there with headphones and talk to someone. But a hearing aid, you can do that. So you can have this form of mixed reality, and that's a really exciting thing for me. So you can, is what people could potentially use this technology for. And right now, hearing aids are just used for hearing aids, and they're not used for anything else. So, I mean, I don't know if any of you have seen that movie, Her, where the guy talks to his AI companion. That's one of the things you can do. You can have something that you talk to all the time. So this thing, because it's Bluetooth low energy, it can be streaming the audio to a phone, which can be processed. Maybe language translation. So imagine you're subtracting whatever the person's saying, and then it only plays the translated text to your ears. Like, imagine that. How amazing that would be. That would be sci-fi, And then, like, stuff that's nothing to do with human communication. Like, maybe you want to do bird ID, or you want to bring the, rumble of elephants that are subsonic, like, into the audible range, and so that you can, hear elephants talking. I don't know. What people want to use this thing for. And then the last but not least, people say, well, this project is doomed because how the hell are you going to make money from this? And I've actually taken a year out. I'm on a sabbatical, a year and a half, to do this project. So it's been a lot of work. And obviously, yeah, something like this is not sustainable. I can't just carry on doing this forever. So I thought, what are the ways in which this project could potentially make money? And that could be, and then I was thinking regulatory and medical certification. So these are very expensive things to do. Imagine this is a really popular project, but audiologists aren't using these things because they're not certified for use. So I envisaged maybe using the name of the project, but then having like a commercial arm that it has a certified thing. So I do have a plan. Whether it's feasible or not, I don't know yet. And that's it. That's it, guys. That's the code. It's the Matrix chat group. That's my email address. Yeah.
Thank you, David. Thank you. That was very insightful. Now we're going to open up for questions and answers. Just raise your hand if you have any questions.
First of all, I really wanted to say thank you because I'm completely dependent on hearing aids, and a lot of the commercial ones are completely uninteresting. They're getting a lot better. In the last couple of years, I've finally got noise suppression. I can finally put my hand by my ear and not hear a squealing sound. It used to be really terrible.
Yeah.
And this is really exciting, and if you need a beta tester, I would love to sign up.
Oh, cool.
I was just taking all your details, but I mostly wanted to say thank you because hearing aids are exciting for those of us who depend on them completely.
Yeah.
And I wanted you to know that I really appreciate it.
Great. Oh, thank you.
Hello. I have to say that I'm very impressed with your entire journey, and I wanted to ask you what would be the best way to contribute to help you to continue this journey for us.
Right. So yeah, the everything is up there on the project. I have, I think, in order to, what I've got to figure out next is a way to bring the cost of this thing down. So my hearing aids are quite expensive to get manufactured, but you can buy this audio dev kit from Nordic. But this is also quite expensive. This is about 170 pounds. So, you know, I need to figure out a way to bring the cost down so that people can actually, you know, buy the hardware themselves.
It's called Kickstarter.
Hey?
Have you thought about Kickstarter or a campaign on Kickstarter?
Yeah, I guess I'll do a Kickstarter thing. Yeah, that's a good idea. Yeah. The components are fairly pricey, like the DSP chip. For some reason, it's more expensive in China than if I buy it here. That's about $18. That's quite a lot for a chip. And the Nordic chip is about $9, and the rest of the stuff's really cheap. So it's not a super cheap thing to make, but it's if I make a lot of them, it's going to be a lot cheaper. So, yeah, I could potentially make them for about £50, maybe. I don't know, but I think more realistically, it'll be about 100. But I don't know yet.
All right, thank you.
Sure.
Thanks very much. Yeah, I'd like to echo, I'm a hearing aid user myself, and it's been kind of pretty life-changing using them. So this is, sorry. Yeah, I think you already mentioned about sort of price point, and I know that, yeah, as the other questioner kind of said, commercial hearing aid technology has kind of improved significantly. The ones that I wear now are a lot better. I don't get the same kind of feedback. There's different kind of modes, kind of like restaurant modes, this kind of stuff. What do you think are going to be have you any idea of the kind of predictable drivers for how prices are going to drop for all these components to kind of, you know, like to increase the facility but keep prices at a accessible level?
One thing I didn't mention that at the start of the talk is my father was actually getting hearing aids, and his hearing aids were $4,000 or something like that. Yeah. So I'm sure, that was just extremely shocking for me because, you know, if you think about what a Bluetooth headset is, like that's got a microphone, processor, and you know, all that stuff in it, but that's $10. Like, what the hell? You know, why are they so expensive? And that was part of the justification for you know, getting involved with this project. So I wanted to bring the cost right down by making something like that. But yeah, so I'm talking about in the realm of, you know, $100 to, you know, hundreds, not thousands. So that's the idea. I think a lot of the cost is regulation, but those are barriers that have been brought down recently. So there's a big push in the States to make to open the doors for lower cost hearing aids and lessen the barriers. I think what I assume happened is the hearing aid companies would have lobbied for higher and higher and more, you know, more regulations, and that's kind of why
that's the thing.
We are.
To what extent is it a cartel? And
yeah, exactly.
Yeah.
So this is why I'm really excited, because I want to make a cheap one that's really good.
Thank you, David. Has anyone used your hearing aid who doesn't normally use hearing aids, either because they've found out through your product that they don't have as good a vision, good a hearing as they thought, or they've got their hearing's fine and they've discovered like a new kind of superpower from what you can do?
No, I'm the only user so far. And I must say I've been testing it in walking around and inside a room, and there's certain things I need serious work, like in a noisy environment. You know that dynamic range where it's moving up and down? It doesn't seem to move down or up or whatever. It's sometimes it's a little bit too loud. So I've only just got the actual DSP stuff working, and it was a big boon for me because I was quite disappointed with when I was working with the software stuff, because I wasn't getting the performance that I needed. And I mentioned the Tympan library, and that's that uses a library called Char Pro and Sig Pro, and those are sort of open source software implemented filters that you can use for hearing aid. And I got them working on the device, but I couldn't get them working real time. So I thought, that's really disappointing. And the reason why they work on Tympan is because that's a 600 megahertz microcontroller. It's a lot more beefy. But it's also, they tweaked it, and they would have used the right settings and all that stuff. And I just didn't put enough time into it. So I probably could have used their stuff. But then I discovered all this hardware accelerated stuff. So I plan to make a hybrid filter where I'm using the DSP stuff and some software stuff combined. Yeah.
Okay, thank you.
Sure.
Hi, thanks for the talk, really interesting. You mentioned power briefly. I'm curious what the sort of power usage of the system you've designed is, and what kind of battery life you can expect.
Okay. Yeah. Another thing I should have mentioned in my talk. The power consumption when it's in standby mode, so it's not streaming audio or anything, is about 70 microamps. So that's like when you turn it off, essentially. And that'll last for more than a month. But when it's on, it's currently using 4 milliamps, which is about the power of an LED, give or take. That gives you about 12 hours of battery. So it's not as much as I want, but I haven't tuned it that much. So there's stuff that I can do with clocks, and there's so much variation, and it's very sensitive. For example, if I turn logging on and it's logging to my computer, suddenly it uses 8 milliamps. So it's important to turn off certain peripherals and to set the clocks correctly. So I haven't, all the power stuff that I've been doing is with the microcontroller and not with the DSP chip. So my next job is to really dig into the power and lowering the power requirements of the DSP chip, because I want something that can last at least 24 hours.
Is that DSP chip, is there a sort of family of them, or?
Yes, I think this one is one of their flagship ones, though. So yeah, but it's designed for this application. I actually think I assume that hearing aids they're probably white labeled. There's probably like an ASIC that they all use, and it's probably like you need to be part of a consortium to buy them, and I just can imagine that's how they set it up. But this proves that you don't actually need an ASIC. You can actually buy off-the-shelf stuff, and you can get something to work.
Thank you, David. Thank you for the talk. I just got a question on from what, as far as I know, for hearing aid, you got one form of hearing is you actually got ear, you got ear canal, and etc. But for some people, they don't have an ear. They depend on some sort of backbone anchor hearing aid. So
yes,
I just wondering is that this version of design would how compatible is that?
Yeah, so this, I think you're talking about maybe a cochlear implant, or you're talking about something that actually, it touches your.
Yeah, yeah.
Right. I didn't actually look into those, but I can't imagine that it would be. Yeah, that would be because that's just the speaker driver that is different. So instead of going in your canal, it's attached to your head. So I guess a different technology for getting the sound into your ear that way. Yeah, that's something I could definitely look into. But I just wanted to build something that was the most common form of a hearing aid.
Yeah. Yeah, that would be good.
the
Yeah,
time
yeah,
being.
because my family members, like, they got lack of ear, so it's like I always look in that area. It's like more option for people in that have disability. Yeah.
Yeah, that's true. Yeah, there's a huge range of different kinds of hearing problems and hearing aids and stuff. Yeah.
But what you're doing is amazing. Thank you.
Thanks.
I think you talked a minute ago about the live testing and stuff like that. What thought have you given to any kind of test harnesses of known audio, known signals compared to a background signals? Is there any kind of data sets that you can use for testing it offline, so to speak?
Yeah, so that's a really good question, and I haven't even started that whole realm. So when I was building the LC3 codec for the audio compression, I didn't have test harnesses, and all I had was my ears, and I would just play the sound. Did it sound reasonable? The Bluetooth consortium kind of keeps their tests sort of a guarded secret for some ridiculous reason. So yeah, I've got to somehow acquire those test harnesses and all that sort of stuff. So yeah, it's one of those things.
Yeah.
There's so much to do.
Thank you.
I was wondering if you were able to test the sync between the two hearing aids you have.
All right.
How well do they sync between each other, and did you have to sync between them directly as well?
No, so they run completely independent of each other at the moment. But if they were slightly more sophisticated, say you wanted to do directional audio and you wanted to subtract, you want to talk to the person in front of you, you're at a busy restaurant, then you want to synchronize, you want to know the phase information, and then they definitely need to communicate and share that information. And that you would use Bluetooth LE for that. So I haven't even looked at that yet, but that's definitely something that's on the list. And that whole three-dimensional audio stuff, for sure. So.
You've mentioned regulation a couple of times and how it's changing, and you had some ideas. Could you talk more about what the landscape looks like and what the to-dos are?
All I know is it's really expensive. Yeah, I have a friend who works, and his whole job is he's just part of a team that does regulation for medical devices. And so at least I know who to ask. But as to how long the process is going to take, all that sort of stuff, I don't know. Which is kind of why I want to build an experimental device that people can use in the interim. And then it's going to be quite some time, quite a few years before. If this does get popular, it'll be a few years before it gets noticed by the industry, and then so I think there's quite a lot of time for me so far. Yeah. But yeah, I don't really know much about that.
Hi. Yep. Fantastic project. Well done. You mentioned something to do with audio mixed reality. I think that's really cool. How much bandwidth do you have on the stream for that? So if you connect it to your phone, could you send an audio signal back and forth?
So for starters, the LC3 codec is it's MP3 quality. It's very, very high quality for its size. And you've got standard Bluetooth LE runs at 2 megabits, which sounds ridiculous because you'd think that Bluetooth Classic is much slower. But the reason why it's so high is so that you can burst the traffic really quickly and then turn the radio off. So you send some data and you turn it off. So you're not supposed to use the full 2 megabits of bandwidth. You're supposed to, just have a stream that's 128 kilobits kind of thing, like we normally have. But yeah, you use a tiny bit of that bandwidth, and of course, if you're sending audio backwards and forwards, you're using 256, so double that. And yeah, so there's plenty of bandwidth.
Awesome.
You've got the whole 2.4 gigahertz range radio. So.
Any more questions? Nope.
Cool. Thanks, guys. Thank you very much. I really appreciate it.
Good afternoon, everybody. Good afternoon. We have another talk from Andre Burgush, Easy Mode Rust. Give him a warm welcome. Thank you.
So as I usually like to do, I'll introduce with a song that will sort of reiterate the things we heard in today's keynote. Come gather us stations wherever you roam, and admit that our numbers have steadily grown. The community's awesome as saints set in stone. So if that to you is worth saving, then you better start teaming up instead of toiling alone. For the times they are a-changing. Come bloggers and writers who tutorize with your pens, and teach those new folks the chance won't come again. Where there once was a newbie, there soon will be 10. And your knowledge is what they are craving. Know that what you share with them is what you will gain. For the times they are a-changing. Researchers and coders, please heed the call. Without your effort, Rust would be nothing at all. And on safety would rise where it now meets its fall. May C++ proponents be raving. What divides them from us is but a Rust up install. For the times they are a-changing. Fellow moderators throughout the land, don't you dare censor what is not meant to offend. Otherwise far too soon helpful people be banned. And what's left will be angry folks raging. Our first order of business is to help understand that the times they are a-changing. The line it is drawn, the type it is cast. What debug runs slow, release will run fast, as the present now will later be past. And our values be rapidly fading, unless we find new people who can make them last. For the times they are a-changing. Thank you. So, easy mode Rust. So I hope that most of you are here because they thought, well, easy mode Rust, that's cool. I think Rust is pretty cool, but I really don't want to learn all that deep stuff. I mean, who here already knows Rust very well? Well, you're in the wrong talk, but anyway, you can, you can stay here. I won't push you out. Well, that's one thing, yeah. But again, this is about how can we teach as little Rust as possible to still make people productive. So you can still pass it on and teach people a small subset of Rust and make them productive with it so they can already do some cool things while learning the rest. So first, some ground rules. We want a really small subset of the language to learn. So we don't want to learn all this high and deep and whatever concepts. And yeah, this means we will have to make some trade-offs. For example, we may lose performance. Sometimes you have to use some of the deep concepts to eke out every last bit of performance you can get. We're not here for that. Because if you're just learning out to do something, you want to be productive as fast as possible. You're not there to win some benchmarks or so. we obviously may end up with more lines of code, because if you're not using all those abstractions, then that's where you'll end up, probably. Oops, that was one too far. And we don't strive for good looks. It's not that we want to write that code that will pass a review from seasoned Rust stations with flying flags, and it's just to get the job done. So we want code that does something useful without learning too much stuff. So now, what are the hard parts that we want to avoid? Oops, let me check that real quick. That's better. So this is the first thing that people run into when they want to write Rust. And I've only picked one example that I have run into in the past, but your example might look different. But mostly it's you have some sharing and some mutation in that code, so you're looking at your items while you're adding to them. So that's obviously not going to fly. Well, let's try to compile that. Oh, that's unfortunate. And not just because I named the crate unfortunate. Of course, the borrow checker is having none of that, which is quite all right. I mean, the rules are there for a good reason. But now, well, we have a problem. We don't want to learn all that stuff. So if we run into that, we want to have a very quick fix so that we can not learn how borrowing rules work and just get on with our life. And the nice thing is we have one immutable borrow and we have one mutable borrow. So perhaps that lets us do something that will fix it easily. Well, there is one thing. We can simply clone our items while iterating over them. And so we will mutate the uncloned items while iterating over the clone. And as such, the link is broken there, so we're iterating one thing while modifying another, so the borrow checker will say, oh, it's all right, go on. Now, some of you may say, well, but all this cloning, it takes so much memory, and I really don't want to do this. This looks awful. Well, I say, first, we're not here for performance or for conserving memory, so please go away. No, just kidding. But in very many cases, the memory is really not an issue, really. But if you really must have a way to do that without the cloning, there is another alternative in that you can simply index instead of iterating over the collection itself, because the index is something, it's just a range, it's just a number there, and you don't borrow until you're inside the loop. There are a few wrinkles here. One thing is that this if predicate is just an if, not an if-let. Because unlike if-let will borrow into the scrutiny, so the items of I here, which would mean that the borrow checker will still complain if you would do that. And also, well, the predicate will have already been run when the then clause of the if is reached. So the modify just modifies this items of I once, and it creates a new item, so it doesn't modify it in place. And then you can push because you no longer borrow items at that point. However, be advised that this is a bit more tricky. It can still fall afoul of the borrow checker. So I wouldn't recommend it. I would recommend to just clone and be done with it. Similarly, if you have data structures that you don't want to borrow in data structures, really. Just have plain values without ampersand stuff. That's also for another reason, to which I will come later. So the next thing that I want to talk to get it out of the way is macros. Of course, calling macros is totally okay as long as you understand what they do. I mean, if you don't, then, well, it's going to be hard anyway, and you have to look into what have you done. Oh, no, that's not what you want. But for example, it will be very, very hard to print something on the console without calling the println macro. So it's totally okay to learn that. Just look at its documentation. It's very thorough, it's pretty good, and it's easy enough to learn, although it's surprisingly complex inside, but let's not go there today, because we don't want to learn this today. We want to learn how to avoid to learn this today. And of course, you don't want to write your own macros, because then you'd have to learn a whole macro language to do that. So we're not here for that. You can learn that later. And if you're really curious, then you can do it right now, of course. But again, we want to be productive first and then learn the rest later. So with some code examples here, we shouldn't write a macro to just remove some code duplication. So if we only have 2 variants here, just copy and paste. It's okay. It's not that much. Yes, you will run the risk that the copy and pasted code gets out of sync. True. But with 2 or 3 instances, I think it should be manageable. And yes, this is a somewhat contrived example, but I wanted to fit on the slide. And yeah, so now some of you might think, what if I not only have 2 or 3 instances of that code, but say 10 or 12 or 100? Why? Then you can simply write code that writes code. This is not a macro. It's a plain Rust function that creates a string with the source code that you would have written. So you only use the normal Rust that you already hopefully know, or that you are ready to learn, because, well, at some point, a few things you will have to learn, and you just create that code from within Rust. No big deal. And yes, I've kept my contrived example, but yeah, in this case, you give the names as an argument, so you can have hundreds of names there, and you will end up with the code that you would have ended up with if you'd just copied it and pasted it 100 times. Now you might say, well, that's all nice, and I like this idea, but what if the names could change and I need to update the code ever so often? Wouldn't I have then to run that each time I need to change something? And what if I forget running it? Then the code will get out of sync with the list of names and all hell will break loose, my code will be wrong. This is nothing I want to do. So do I now have to write a macro? Well, no, you can just write a test. In this case, the idea here is that you have another plain Rust method that reads the code as it is currently. Then you create the code. Okay, now we only have 2 names here because 100 wouldn't have fit on the slide, but yeah. And then you check if it's still the same. If it is the same, then you're finished. You don't have to do anything. But if it's not the same, then you can just rewrite the code. You can change the code, update it, and panic so that whoever ran the test knows they need to commit the changes. Pardon. I got this technique from a blog post from Alexei Kladov. So to reiterate, ignore macros for now. If you can copy the code, if that's enough, just do it. If you need to generate code, just generate it from plain Rust code. And if you need to keep it updated, use a test for that. Because you'll want to be able to write tests anyway. So this is something you should have learned. And it's not that hard. You just push a test annotation on a function, and there you are. Also, I noticed that I've called a macro in there, the panic macro. But you should already know that. You can call it as you would call a function, and it will just crash your code with a suitable message. Now, traits. Traits are crazy powerful. And really, you can do a whole lot of stuff with traits. But they're also kind of complex. So of course, we want to avoid that if possible at all. At some points, you might need to have a trait for something. For example, if you have a type that you need cloned at some point, then you can derive clone on your type. That's easy enough. That's one small thing to learn. It's not that complicated. The clone implementation will be automatically generated for you. So that's not that complex. But this is for traits that are general and that are common. Not all traits can be generated, but if they can, it's a very good solution to do. Now, you might also use traits to disambiguate some cases. And in that case, well, you can also just use a bag of if clauses and do this case disambiguation at runtime. Yes, it will cost performance. Yes, it won't be that nice as just have a trait dispatch, but it will be easier and you'll get the job done. Unfortunately, some frameworks force you to implement a trait. And yeah, in that case, there is no option then either to ditch the framework or to just do it. In that case, I would suggest if you have an IDE or some good editor with, say, Rust Analyzer or something, then you can use the IDE to generate at least a stub for the trait implementation, and then you just fill in the blanks. And you don't really need to know what it does then. Okay. Now, with traits, there comes another topic here, that is generics. So for example, if you have a struct that is implemented to be generic over some types, well, that's, or a function that is generic over some types, well, that's also quite a powerful idea, but on the other hand, it's interesting to learn about that, but we don't want to do that here for now. So we want to keep it very, very simple. And here the solution is also very simple. We just built a plain foo AB struct or a plain foo AB method for each AB combination we want to do. And again, you might have many, many AB combinations there, but this is just a case for our macro replacement. We can just generate those. Because if you would implement a generic method there, it would also be very similar for each type. So yeah, it should be a prime suspect for macro generation, or for code generation. Now, another thing that stumps many beginning Rustaceans, lifetimes. oh my gosh, what are those ticks? And well, let's ignore that for now. We don't want to learn lifetimes. I mean, they're cool in that they let us express some things, but we're not here to make full use of the type system or write various high-level shenanigans. We're just here to get the job done. So if we really need something that has one single identity and doesn't change upon cloning or upon copying, then we can just use an arc instead of a reference there. And yes, this will have a runtime cost. So you need to clone an arc to reuse it. And yes, that will update the reference count, so your code will be slightly slower. Also, the second thing is, what arc does is basically move the borrow checking to runtime, so you might run into runtime errors that would simply be compile time errors with references. But as long as you keep the stuff simple, and again, we've just learned a few lines of Rust, so we're not into deeply complex stuff. So we'll keep it simple. It will usually work. And again, even if you don't use Arc, you can, for some simple things, you can just use the plain types themselves without references and just clone it if you don't care about the identity of the objects. If, of course, you want to mutate things and be sure that it hasn't been copied in the meantime, then you need to do things like an arc. So that's already gotten rid of a lot of things that people struggle with. Still, well, I could end the talk now, and this would have been a very, very short talk, but I still have a few things. But it's short. So unless you do embedded development, you won't need any unsafe. In, I think, at least 90%, perhaps more, of cases, you will get very acceptable performance with safe code, and there's literally nothing you cannot do with safe Rust. Really, literally, unless you are on embedded and don't have full platform support. Usually, everything you want to do is possible with safe Rust, period. So, no unsafe here. Same thing for SIMD. Hey, we're not for performance here. So let's ignore that. Why did I add that here? Well, forget that you saw that. It's not a part of Rust you want to learn right now. So we have no generics, so we don't have higher kind of types. Now for the elephant in the room. Again, like other things on this list, async Rust is really, really powerful. But we're not after powerful. We're after simple here. So avoid if possible. However, if you cannot avoid it, because sometimes you really want to use some crates or some frameworks that require you to use async. For example, if you use Exum or Actix or any of the web frameworks that are so common today, you will have to write async functions. So sometimes you will need to write async code. Unfortunately, we cannot completely avoid that. So if you can avoid that, if your dependencies don't ask you to write async code, just don't. Just write plain Rust code, it'll be fine. But if you want to do something where you need to write async code, then you just relax. You prepend async before your function signature. And whenever you have a function call in your code, you just append a wait on it. So that's even if you know that the function call will probably not be an async function, just await it and let the compiler deal with it. So if the compiler tells you, well, this is not a future, you cannot await it, then you remove the await. But just by default, just await everything and let the compiler sort it out, because it's easier this way than the other way. So if you fail to await every function call, then you might have the chance where you call this function, but all it does is return the future to you and you do nothing with it. And that's something that's not that easy to debug. It will nowadays get you a warning that you should do something with that future, but even then we would need to learn more about async than we want to know right now. And so this way is certainly easier. So rather than letting the compiler tell us, oh, you need to await this, just await and then remove the await if the compiler tells you not to do it. Also, one thing that people run into, and I ran into that last week, and I'm not a newbie in Rust, but well, sometimes it happens. If you have some things that block, like a mutex, an RW lock, or conva, or whatever that might lock, be aware that blocking something within a task, within an async task, will block the whole thread. So this is something that can very, very easily deadlock, even if you're not intent to do that. So in async Rust, we must rid ourselves of the notion that our code runs sequentially, or you know where it starts and where it ends. It may run whenever. So avoid blocking things. If you really must have some synchronization, then use the synchronization primitives of the async runtime. Most runtimes have things like mutexes, channels, stuff like that. So use them if you really must. Otherwise, try to avoid synchronization if possible. That's another thing that trips people up. Modules and imports. So what I've seen is, and I've slightly exaggerated this, having one very, very large file and you can no longer navigate in it, and this is not tractable. I mean, I cannot navigate in a 20K lines file, let alone 100K, and yeah, so how would I find anything there? I mean, yeah. Perhaps with some machine learning or so. I'm not sure. Or the other thing is you get 10,000 files that are just a few things and they're deeply nested, and then you get lost in its structure, and at the worst case, some of those files are named the same, and then you have all those .modrss in your path, and your editor tabs are open with, oh, you don't know what is what. So let's avoid that. And again, we don't want to learn how modules and imports work. I mean, at some place we want to learn a bit of it, but we want to keep it simple. And the big problem is that modules and imports, they conflate the code organization with a path hierarchy. So you have paths in your code. Those are built by the crate and the nested modules and whatever items are in there. And you want to organize your code into different files so they don't get too big. But yeah, if you just split them up, then the items will have been moved within the path hierarchy. So let's split those two things. This means that when you change your code, you will have to do multiple steps at once, but that way you cannot run into the problem that, okay, I moved code, now my users can no longer compile because the code has moved. So for my example, I have these two things. I want to split the code without splitting the paths. So that would be the first thing. So for my example here, I have two methods that are very long, so they could fit on the slide. in practice, those could be 1,000 lines long each, or you could have multiple methods, but I'll keep it simple for the explanation here. So the first operation is we want to split this. We want to put, say, B into a b.rs file, into a submodule, and import it from the librs, but in a way that someone using our crate will still see the A and the B on the librs, so on the crate root. And so we can do exactly this. We have moved B into our BRS and replaced it in librs with a mod B and a pub use B : B. So we forward the visibility. Within B, RS, the function is public. Otherwise, we couldn't pub use it. So the function and the use must have the same visibility. And I would suggest you only use pub or nothing, because again, we want to keep it simple. No weird qualifiers in there. And by doing this, from the outside, it looks exactly the same. We have a crate that has an A function, that has a B function, nothing else. And we have two files, so we can modify B to a heart's content without having to look at A and vice versa. Note that we don't make the B module public though, because otherwise we would have an A function, a B function, and a public B module that also contains the same B function. And now let's say the other thing. We now have split B off, and now we want to move it into a B submodule, actually, for our users. So this is a breaking change, but perhaps at some point our crate has grown unwieldy and we think we need to add a bit more structure in there, so we'll introduce that B submodule publicly. Luckily, we've already split the code in one way, and so we can easily do that. So we delete our pub use there, because the B function should no longer be in the crate root, it should be in the submodule. And now we make the submodule public, so it's now pub mod B instead of mod B. By doing this small change, for our users, we've used the B function from the crate root to the B submodule. And that's it. So those two changes are, well, I would hope to say, perhaps not very easy, but easy enough to not get wrong. And if you do it that way always, you'll never run into the problem that you inadvertently change the interface of your crate while moving code around. And you have a way of moving code around, of changing the interface if you want to. And of course, in this case now, callers will have to call B : B instead of B directly. Now, Rust is known as a very expressive language, so it has a lot of syntax. There are many languages that are easier from the syntax point of view, but you don't need to learn all of that. So mostly keep to if, for, and while, or perhaps whilelet. And the other things, if you need to use them, use sparingly. So match, again, like many things in Rust, is crazy powerful, but it's also harder to learn. So you can use it, but avoid the more complex things like pattern guards or nested patterns. Those are things you don't want to do, obviously. And one thing that I always get from people coming from languages like C or C++, is Rust is so hard because try building a doubly linked list. You won't be able to do it. Well, I don't need to. I already have a doubly linked list in the standard library. So don't implement your own data structures. There's really no need to. You don't even need to learn all the data structures. So a simple thing is, if you have data that is continuous, like a list, you have 1, 2, 3, whatever, a number of items, then you use a vec. Simple as that. No need to learn all higher-end data structures like vecdeck, binary, whatever. No need. And also, even if you only have one element, you can still put it in a vec. Who cares? I mean, again, we're not after performance here. If you have a thing that looks like a dictionary or lookup, like something with a key and a value, so if your key is recursion, then the value is please look at recursion. That's anyway. Then you use a hash map. Simple as that. Yes, there's a small caveat. If the type you want to have as a key doesn't implement hash, well, you might need to switch to a B-tree map then, but for 95 to 99% of cases, hash map will work fine, and let's not make it too complex here. Wow, this is also something that might come up. I want to return an iterator. No, you don't want to return an iterator. You just collect your things and you just return the collection. If you iterate into a serial collection of things, just return a vec. If you iterate into a key value pair of things, you might return a map instead. But if you really need to return an iterator, then you can box it like this. Yes, this is more complex, but you don't need to learn it. You just need to know that this line here, you have iterated something without collecting it. Just remove the collect there, and then you box it and return it as box of the iterator, and you need to specify the item type there. And there you are. But again, this is only as a last resort because let's say your iterator is not bounded, so it would collect forever and fill up all available memory. So just for those cases, you really need to not iterate right away. In that case, you can do that. And that's all. So congratulations, you no longer have to learn Rust, but feel free to do it anyway.
Thank you, Andre. I'm sure that will be helpful to many new Rust stations around the world. We're going to have we've got quite a long time for questions and answers, so fire away if anybody has a question.
Oh, that early.
So thank you very much for this. As somebody who's done a bit of Rust education targeted at, shall we say, the more expert programmer, I would really like the things in this talk to be incorporated in early teaching materials. Have you written them up somewhere? Can we make references to them?
Unfortunately not yet, but I will certainly blog about this in the near future.
Yes, please.
Hello. So you kind of alluded to it at the end of like, oh, well, follow all these tips and you won't need to learn Rust in the sense of like, then what is the benefit to a new Rust station for like using Rust if you're not going to use many of these powerful features that Rust has? And as a project matures, in your opinion, what's the right time to start replacing some of the workarounds with the more idiomatic Rust techniques?
Well, thanks for asking that. That's a very good question. The thing is, this talk's not about completely avoiding to learn Rust, but it's about getting you started as fast as possible, because this is something that many people find off-putting. They don't want to learn Rust. They say, okay, I will have to work super hard for learning it, and only then will I get the benefits. And even if you do all those things, you will still end up with acceptable performance in a great big number of cases. You will still end up with acceptable code that is also very easy to parse because it's very simple, doesn't use a lot of things, and yeah, it's very easy to know what's happening. And it will probably also compile pretty quickly, so that's also a benefit. And the thing is, you want to be productive. You want to be able to write code from the get-go. And I must say that I personally was in a very lucky situation. When I learned Rust in 2015, there wasn't so much learning material, but for good luck, I chose to write a lint for Rust. And the nice thing with lints is that the compiler already owns everything. So you don't need to care about ownership or borrowing or stuff. You just write your code very plainly. And so I think I was about 6 months in before I wrote my first lifetime annotation. So, and if you do it the way I told you here, you will have the same experience. You can learn lifetimes on your own terms, whenever you need them, whenever you want them. I mean, I'm a very curious person, so I learned pretty quickly. But so you can set your own time to learn whatever you want to learn, and then reap the benefits, obviously. And it's never too late to just improve your code. And again, those things are just for avoidance of learning large swaths of the language. And you don't need to do that for always. I mean, it's just to get you started. And some of this advice actually counters things that I would advise you if you were to write idiomatic code. So, for example, with idiomatic code, you often want to avoid cloning. Where for easy beginner code, clone wherever you want. So that's the big difference here.
Thank you for the talk. I find it very interesting, especially from your perspective, being somebody that's helped mentor and teach so many people that have their first question that's being asked in a lot of forums. I know you moderate many. So this is coming from that perspective. I was curious your intuition about the importance of material that is aware of newcomers using a text editor rather than an IDE. And whether you sort of frame these suggestions to be conscious of people who aren't using Rust Analyzer or Rust Rover.
So if you use Rust Analyzer, then that's great. It will certainly help you, even if you don't use all the parts of the language. And I think at one point I even told you to use an IDE where possible. So I would not suggest you need to go use a plain text editor because it will make things simple. That's really not needed. If you can use an IDE, then by all means do that.
I mean, when you see people who are trying to do it all on their own and they're asking their first question, do you see many people that are just using a text editor? Yeah.
No, that's... I think the population of Rust newbies plainly mirrors the population of other Rust users there, that most people use VS Code, some use Rust Rover or some other tools. Some might use Vim or NeoVim or Helix or Emacs or what have you.
Yeah, thanks for the talk. I might have a couple of people coming into our team soon who most likely haven't done Rust before, so this is interesting stuff to think about. About the subject of fallible operations, so operations where in other languages you might throw an exception or raise an error, and idiomatically in Rust you'd return a result. along the same lines as what you've said elsewhere, would you just say like unwrap everywhere? Would you just use anyhow, like you create anyhow? Like what would be your approach?
Well, it depends a lot on your use case. I think unwrapping, for example, in tests is absolutely fine. So if you have a new team member that's going to start by writing tests, have them unwrap everywhere, and they'll be fine. Also in tests, it's easier to debug because you get a good backtrace, whereas if you return a result, you will only have whatever the result gives you. And so that's one thing you can do to avoid well, doing the idiomatic thing, but a bit more complex thing. But on the other hand, well, actually, I didn't talk as much about using result. I think in that case, I wouldn't hold off that long from learning it because it's such an intrinsic thing to the language that it's a good idea to learn it early.
I'm going to second his point about, your point about wanting it all. I think I would love to have a poster of this to put, like, when there's a hack and learn, just put a poster on the wall of like, hey guys, just like, this is cool.
So, well, I'm probably not that good at typography, but perhaps someone who's good at that might talk me up later and we'll manage to make something.
And then the other thing, yeah, like having a protest song in a Rust conference feels right to me. This is good.
Thanks for the talk. I want to second both their points because as someone who started Rust not too long ago, trying to wrap my head around why can't I find anywhere online about exceptions getting thrown and how do I handle that, it took me a really long time to process it. Regarding your slide on the loops, would it be helpful, or do you think it'd be helpful to add something about iter versus into iter? Because that's something that I did struggle with a lot. I have a Stack Overflow page bookmarked, so I remember which one to use all the time.
Yeah. So that's really kind of a hard one because that kind of meshes into borrowing and lifetimes. So I would use iter, or, well, you don't, if you have a vec, if you have a simple collection, then you won't need to call into iter, but you just iterate over the vec. And if the borrow checker complains, then you need to clone. So those are the two rules that I gave you. So you just iterate over the collection directly. If then Rust tells you, okay, but you've used up the collection, you've consumed it there, then just add clone and you can reuse it, no problem. And you are done. No need to call iter or into iter.
Thank you for the talk. So if you imagine you have a situation where you have senior developers and developers starting out contributing to the same code base and doing PR reviews. So how do the senior devs handle like the not so idiomatic Rust being committed to the same code base?
Yeah, I get where that comes from. And yes, this is a really, really hard question. And my advice would be, especially in the beginning, just merge that code and clean it up later. Have some intermediate Rustation clean it up at best, then they get more practice in doing that stuff. And the new Rustation has the benefit of having gotten their own change into that project, and that feels great, and they're motivated to keep at it and learn more and get better, and they'll probably become a steady contributor and get better with time. And then you can start teaching them the more advanced things, and as they go along, their code also will become better, and they'll be the intermediate ones fixing the problems that other newbies introduce, and so it's a virtuous cycle. And as in many cases, the human factor often trumps the code factor. especially in volunteer-driven projects. If you are in a company, then that might be different, but even there I would try to motivate my co-workers as far as possible.
Thanks for the talk. I was wondering if there's some kind of formal structure around the advancedness of features. So if you imagine like a flat list of all the Rust features, when a newbie comes, it's like, oh, this is super complicated, which one should I learn? Whereas like another complex language like Scala, the language designer sort of made 6 levels. So sort of like beginner, application, intermediate, advanced, and then library level beginner, and so on, which kind of sets some expectations. So you think, okay, I'm going to focus learning these things on the first level, and then level up, and then level up again. So, you know, you can avoid things which really you don't need until later in your journey. Is there some kind of resource within Rust for that?
I'm not completely sure. The problem with that is that Rust is much more versatile than Scala. You can use it to do very high-level stuff, you can use it to do very low-level stuff, and even within low-level stuff there are many differences. For example, you can go into wrangling SIMD instructions, eking out the utmost of performance, or you can go into embedded and have one certain architecture that they are working from. I hear that some people run Rust code on their C64. That is something that Scala probably cannot do. And so with many of those topics, you can go arbitrarily deep, but you don't need to. So it depends very much on what you want to achieve. With that said, I could imagine something like an experience tree that some games have apparently, where you can say, okay, you learn this and then you unlock this with that. This is something that might be a possible thing, although it's probably not that easy to set something like this up because you need a very diverse set of backgrounds to do it well. But I think I could start with something and then have other people fill in the blanks. So as a group project, that would be pretty cool.
Sounds like a nice open source project.
Yeah, exactly. So I'll be glad either to do that at some point, or if any of you wants to do it, I'll chime in where I can. Just ping me.
Yeah, interesting talk. I find the code generation aspect interesting because it's certainly way easier to write string manipulation code than to learn the whole new either macro or macro by example, which both have their intricacies. But I wonder, like, what's the good way to integrate that with your project? Because, like you mentioned, like a test thing, but I'm still trying to imagine, like the simple case is just you have a separate binary that generates the code, then you copy it over. But then how do you integrate a test case?
Yeah, so the thing is, first you create that function that generates the code, and then you can simply copy it over to the playground. I have some binary that runs it, and then you run it once, and there you have the code. Okay, fine. But at some point you might have to update the code with changing requirements, and that's where the test comes in. So basically what you do is you copy your code creation function nearby to the test case. You'll have a normal test case there. It's just a test annotated function within your code that will open the source file, find the beginning and end of the code you want to create, snip it out, compare it with the code you would generate, and if that's different, then the test fails. It will also write the changed code. You need to keep the prefix and suffix for that and put it together again, but that's also easy string manipulation. And then you also fail with a panic message asking the caller to commit the change that the test just made.
So that's still in that separate generator program, the test tool.
No, it's just a plain Rust unit test.
Right, because there's
so
like
this is within your code. You have a test within your code that will generate the code or regenerate the code. if needed.
Okay, so it's in the same.
So basically, it's self-modifying code.
Okay, so it's
But
in the
at
same
test
code base.
time, not at
Interesting.
runtime.
I wonder if there's like a framework for that.
Actually,
It seems like
there's-
something that could
there's
be
really
abstracted over.
There's really very little need for such a framework. Again, I will blog on these things in the next 1 or 2 weeks, and I will link the article I got the technique from that will explain more than I could do in this short talk. But the structure is always the same. You read the code as it is, you generate what you think the code should be, you compare it. If it's different, then you write the code, the changed code, and you fail with a message to commit.
I'm just inspired by the levels of complexity type thing. I'm wondering whether you could have like different, like a clippy -- beginner, which would not necessarily select which rules, but select which suggestions it gives, right? So it's not going to try and teach you
actually,
something
we
you don't
already
know.
have that in a way because there are some lints that are geared towards beginners that are always active because, well, experts know how to deactivate them. So in a way, all Clippy lints are for beginners and sometimes experts alike. But in some cases, well, we have some lints that if you want to switch them off, you know how to do it. So, yeah.
I wanted to follow up on all the string manipulation stuff. I think passing plain strings around is something we neglect when we have the power of new types and from and all this stuff. So it reminds me, I'm going to pair this with the errors in result handling to reference Figma's blog post about how they introduced Rust. And the way they did was the error result was just plain string. So whenever you do error, you just do error format as the return, and that was the way they started integrating. And this was before anyhow and this error, but I still think that approach is easily upgradable to anyhow in the long run.
Yeah, that's a very good point. Thank you.
Any more questions? Nope. Oh, I'll wrap it up there.
Still have time for one question.
Thank you again, Andre. Can we give Andre a round of applause? Thank you.